The bone appears first as a pale curve in the desert floor, not a skeleton, not even a shape that looks, at first, like an animal. Just a thickness of stone-colored material pushing through the dry ground of Patagonia, weathered by wind, half buried in sediment, too large to make immediate sense. A person walking past it might see only a strange rock. A ranch worker sees enough to stop. The surface is not like the rocks around it. It has texture. It has a curve. It has the quiet wrongness of something that once belonged inside a living body. Around it, the land is open and low. The hills of Chubut rise in worn layers, and the wind moves dust across the ground the way water once moved sand through these basins. There are no forests here now, at least not the forests that lived here in the Cretaceous. There are shrubs, dry gullies, fences, ranch tracks, and outcrops where the past sits close to the surface. But in one place, at La Flecha, a single exposed bone was enough to call paleontologists into the field, and the field would not give them one animal. It would give them many. The animal, eventually named Patagotitan majorum, was not discovered as a complete body lying neatly in one place. Giant dinosaurs rarely offer that kind of clarity. The fossils came out as a collection of enormous bones from several individuals, scattered through layers that had once been flood deposits. Femora, vertebrae, ribs, pieces of limbs and body architecture so large that each one required planning, plaster, and machinery. The animals had died in separate events, or at least had been buried in more than one layer, and the quarry preserved a repeated pattern of loss on the same ancient landscape. The first time scale enters the story, it does not arrive as a number. It arrives as size. A femur longer than a person is tall. A vertebra that looks less like a backbone than a carved block from a ruined building. A rib that curves with the span of something architectural. Each piece is biological, but it seems to have crossed into the language of geology. These were not sea animals floating in water. These were land animals, carrying their weight on four limbs, breathing air, moving across floodplains, lowering their heads to feed, raising them into a Cretaceous sky. If these journeys into the dinosaur age are what bring you back, subscribing keeps the next one close. Patagonia has become almost inseparable from the question of dinosaur size. This is not because every giant dinosaur lived there, and not because every Patagonian fossil belongs to something extreme. The region is vast, and its fossil record includes small animals, predators, turtles, crocodiliforms, pterosaurs, plants, eggs, footprints, and bones that have nothing to do with the largest creatures on land. But again and again, from the Cretaceous rocks of Argentina, paleontologists have recovered remains of sauropods that push against the upper limits of what a land animal can be. Some of these names have become famous: Argentinosaurus, Patagotitan, Dreadnoughtus, Futalonctosaurus, Portosaurus. Others are less familiar outside paleontology, known from fewer bones or from papers read mostly by specialists. Together, they form a pattern that is difficult to ignore. During the Cretaceous, southern South America supported a diversity of Titanosaurs, the last great branch of the sauropod lineage. Some were moderate in size, some carried armor in their skin, some were comparatively small by sauropod standards, and a few became so large that even describing them in ordinary measurements begins to feel inadequate. A number like 50 tons is easy to say. It fits in the mouth cleanly. But the living animal behind that number is harder to hold in the mind. 50 tons means bones under constant stress. It means a heart pushing blood through a body that could stretch more than 30 meters from head to tail. It means feet compressing mud so deeply that a riverbank might keep the impression after the animal moved on. It means an animal so large that the space beneath its belly could feel like shade. Titanosaurs were sauropods, and sauropods were not new animals by the time Patagonia produced its most famous giants. The basic sauropod body plan had deep roots in the Mesozoic. Long neck, long tail, Small head. Massive body. 4 column-like limbs. A feeding strategy built around taking in large amounts of vegetation rather than chewing food into fine pieces. During the Jurassic, sauropods had already become some of the largest animals to walk the earth. But Titanosaurs carried that story into the Cretaceous and, in several lineages, took it even further. The question is not just which dinosaur was biggest. That question attracts attention because it feels simple, but it is not simple at all. The deeper question is how Patagonia could preserve so many animals near the edge of terrestrial possibility, and why the southern continents, in the Cretaceous, became a place where titanosaurs flourished with such variety. To answer that, we have to move between a quarry face, a floodplain, a museum mount, and the bones themselves. Imagine the fossil not as an object in a display hall, but as it first appears in the ground. The desert surface is rough, the air is dry. The exposed bone has been wading through seasons of heat and cold, while wind strips the softer sediment grain by grain. Someone kneels beside it. A brush moves dust away. The pale surface widens. The curve becomes part of something larger. What looked like an isolated piece of stone becomes a signal from an animal that died before the Andes had their modern shape. Patagotitan lived during the early Cretaceous, roughly 100 million years ago, in what is now Chubut province. The rocks that held it belonged to the Cerro Barcino Formation, part of the Chubut group, a sequence of continental sediments with rivers, floodplains, lakes, and volcanic ash contributing to the record. The environment was not a single unchanging scene. Rivers shifted, floods came and went. Ash fell or was washed into basins, soils formed and were buried. Animals died in places where sediment could cover them before weather, and scavengers erased the evidence. The living landscape would not have resembled the dry open ranch land that surrounds the fossils today. There were channels, wet ground, plants growing along watercourses, and patches of vegetation that could support enormous herbivores. Flowering plants were becoming increasingly important in the Cretaceous, but conifers, cycads, ferns, and other older plant groups still shaped many ecosystems. The Patagotitan herd, if herd is the right word, moved through a world where familiar plant families and ancient ones existed side by side. It is tempting to imagine 6 Patagotitan individuals dying together in a single disaster, but the evidence points to something more layered. The bones come from distinct levels, suggesting repeated burial events rather than one simple mass death. This matters because paleontology is often strongest when it resists the easy picture. A dramatic scene can be useful, but the rock usually tells a quieter story. Animals died in the same general area at different times. Floods moved sediment over them, their bones entered the ground, and later bodies entered the same record. The name Patagotitan Maiorum carries both place and gratitude. Patago refers to Patagonia. Titan evokes great size. The species name honors the Mayo family, owners of the ranch where the fossils were found. Scientific names can sound remote, but this one preserves a chain of human events as well as ancient biology. A ranch, a discovery, field crews, preparation labs, comparative anatomy, a formal description after years of work. Before a dinosaur becomes a name, it is a logistical problem, a scientific argument, and a set of bones that must be carefully freed from stone. In the lab, the scale changes again. A bone that looked enormous in the field becomes even more difficult indoors. Plaster jackets have to be opened. Rock is removed with tools that may work for days on a few centimeters. The fossil cannot be rushed. A fracture line might run through a limb bone. A vertebra might hold delicate surfaces that preserve muscle attachment scars. Every scrape matters, because the difference between stone and bone may be subtle, and because once a surface is damaged, time cannot put it back. When researchers estimate the size of a giant titanosaur, they do not simply measure one bone and declare a winner. Several methods are used, and each carries assumptions. The circumference of weight-bearing limb bones can be compared with living animals and other dinosaurs. Digital reconstructions can estimate body volume. Comparisons with related species can fill in missing portions, though those comparisons become less secure when the fossils are fragmentary. In the case of Patagotitan, the relative completeness of the material makes it one of the most important giants, even while its exact mass remains debated. Early estimates placed Patagotitan near 70 metric tons. Later work and alternative reconstructions have suggested lower or broader ranges, sometimes closer to the high 40s or 50s, sometimes still allowing a much higher value. That uncertainty is not failure. It is the scientific process applied to an animal with no living equivalent. A mounted skeleton can look final. A number in a headline can sound final. But the animal in the rock is more complicated than either the mount or the headline. Argentinosaurus shows the problem even more sharply. It may have been as large as Patagotitan or larger. It may have been among the heaviest land animals ever known. But the fossil material is much more incomplete. A few enormous vertebrae and limb elements can reveal immense size, but they leave more of the body open to reconstruction. The result is a dinosaur that stands near the center of every discussion of maximum sauropod size while remaining frustratingly partial, known more by the magnitude of its fragments than by the completeness of its skeleton. One vertebra can carry a whole animal in imagination. For Argentinosaurus, the backbones are so large that the spaces inside them become part of the story. Sauropod vertebrae were not solid blocks. They were invaded by air spaces connected to the respiratory system, reducing weight while preserving strength. In an animal of ordinary size, this might seem like a detail. In an animal approaching the upper limit of land life, it becomes essential. Without lightened bones, the neck and torso would be even harder to support. Sauropods likely had an air sac respiratory system similar in broad principle to that of birds. Air sacs extended through parts of the body and into many bones, leaving a skeleton that could be both large and lighter than a solid version of the same structure. This system also made breathing more efficient. For giant animals, efficiency matters at every level. The lungs must supply oxygen to tissues spread across an enormous volume. The skeleton must resist bending and compression. The body must move without spending more energy than feeding can replace. The neck is the most visible part of the problem. A titanosaur neck may look graceful in a museum, but in life it was a massive structure made of vertebrae, ligaments, muscle, blood vessels, air spaces, and skin. It had to be light enough to carry, strong enough to use, and useful enough to justify its cost. A long neck allows a sauropod to feed over a large area without moving the whole body. It can reach high vegetation or sweep across lower plants, depending on the species and posture. It turns a stationary animal into a feeding radius. Not every titanosaur held its neck the same way, and not every sauropod fed in the same manner. The old picture of all long-necked dinosaurs stretching straight upward into treetops is too simple. Some probably fed higher. Others may have browsed at medium height or moved the neck across a broad horizontal arc. The fossils give clues through limb proportions, vertebral joints, muscle attachment areas, and comparisons with related animals. But posture in a living animal is dynamic. A neck is not a diagram. It moves. Titanosaurs had small heads relative to their bodies, and that smallness was not a weakness. A lighter head makes a long neck easier to support. Their teeth were usually simple compared with the grinding teeth of many mammals. They were often suited for cropping or stripping vegetation, rather than chewing it thoroughly. Food could be gathered quickly and passed into the digestive system, where fermentation and long gut residence times did much of the work. This is one of the great differences between a sauropod and a large mammal herbivore. A living Patagotitan feeding beside a river would not have chewed like a horse or a cow. It would have taken plant material in repeated motions, stripping branches, pulling foliage, cropping whatever suited its mouth and height. The jaw would move. The neck would adjust. The body might remain mostly still for long stretches because moving 50 tons is expensive. Insects would lift from the plants. Leaves would fall. Mud would take the weight of the feet. A feeding animal of this size changes the landscape simply by being there. Size provides advantages. A full-grown titanosaur would have been difficult prey for most predators, even very large ones. A juvenile was different. Eggs, hatchlings, and young animals were vulnerable, and the fossil record of titanosaurs elsewhere in Argentina shows that reproduction involved eggs laid in nesting grounds. At sites such as Auca Mahuevo in Nucún province, titanosaur eggs and embryos have given rare evidence of sauropod reproduction, including embryos with skin impressions. These were not the eggs of Patagotitan specifically, but they reveal part of the broader titanosaur life cycle. The contrast is striking. A giant adult may have weighed tens of thousands of kilograms, but it began inside an egg small enough to be held by a person. The animal did not hatch as a miniature giant in any meaningful sense. It hatched as a vulnerable body in a world of predators, droughts, floods, disease, and chance. Most probably never reached adulthood. Gigantism is often described through the animals that succeeded, but the living population would have included many failures, many vanished young, many bones too small or too fragile to preserve. Growth had to be fast enough to move juveniles through the most dangerous size classes, but controlled enough to build bone that could support a future giant. Studies of sauropod bone histology show rapid growth in many species, with tissues that record an animal expanding dramatically during its early life. For Dreadnoughtus, the bone evidence suggested that the known individual was still growing when it died, despite already being enormous. That detail is almost more unsettling than the mass estimate itself. The animal was not finished. Dreadnoughtus schrani comes from southern Patagonia, from upper Cretaceous sediments in Santa Cruz province. It is famous not because it is certainly the largest dinosaur ever found, but because it is unusually complete for an animal of its size. Much of the postcranial skeleton is known, along with additional remains, giving paleontologists a rare opportunity to examine the anatomy of a truly gigantic titanosaur in detail. Most giant titanosaurs are known from isolated or partial bones. Dreadnoughtus offers more of the body. Its estimated mass has been debated. The original description suggested a value around 59 metric tons, while later approaches have proposed different numbers. But the argument over the exact mass should not obscure the importance of the specimen. Dreadnoughtus shows the shape of a giant more clearly than many larger, or possibly larger taxa. It preserves limbs, vertebrae, ribs, and other elements that allow researchers to study proportions, posture, muscle attachment, and growth. Sometimes the best fossil is not the biggest one. Sometimes it is the one that answers more questions. The name Dreadnoughtus means fearing nothing. It refers to the animal's size, the idea that a mature individual would have had few enemies. Yet the animal died. That is the quiet correction built into every fossil. No size is permanent. No body escapes the landscape forever. The bones of Dreadnoughtus were found because the animal entered sediment, because decay and burial happened in a particular sequence, because erosion later exposed the rock in a form people could recognize. Fossils are often treated as discoveries of animals, but they are also discoveries of circumstances. For a body to become a fossil, it must avoid being completely destroyed. It must be buried quickly enough or protected long enough. Minerals must enter the remains. Sediment must harden. The rock must survive uplift, erosion, weather, and time. Then it must be exposed at the surface, but not so long that it crumbles away. A dinosaur can live for decades and vanish entirely. A single bone can survive 80 million years because the conditions aligned. Patagonia is good at producing these alignments, not everywhere, and not always, but often enough to make the region one of the most important dinosaur landscapes in the world. The Nucún Basin, the Chubut Group, the deposits around Lake Borealis, the fossiliferous rocks of Rio Negro and Santa Cruz, all preserve different parts of Cretaceous life. Rivers carried sediment. Volcanic ash helped date and bury layers. Floodplains trapped bones. Erosion later opened the record. The giants did not appear from nowhere. They came out of basins that recorded them. Phytoloncosaurus duce gives another window into that record. Found near Lake Borealis in Nukun province, it belongs to the late Cretaceous and is known from a comparatively informative skeleton, including a complete neck, dorsal vertebrae, ribs, pelvis, and other material. Its name has been translated from Mapudungun roots as something like giant chief lizard, and the animal deserves that sense of presence. It was not just another large sauropod. It was a body that helped fill in the anatomy of giant Titanosaurs when so many others were known only in pieces. The site that produced Phytoloncosaurus also preserved other animals, giving the fossil more context than an isolated bone would provide. There were remains of other dinosaurs and evidence of a landscape shaped by water, vegetation, and burial near a Cretaceous lake or river system. A giant sauropod is never alone in a useful scientific sense. Its body belongs to an ecosystem. Its bones appear with sediment, plants, smaller animals, predators, and the chemistry of the environment. To understand the giant, you have to understand the ground beneath it. The predators of these worlds were not small. In mid-Cretaceous Patagonia, Carcharodontosaurids reached enormous sizes. Titanotitan from the Cerro Barcino Formation, Giganotosaurus from the Candeleros Formation, and Maposaurus from the Huincul Formation all speak to a southern predator guild that could rival any in the Mesozoic. These were not tyrannosaurs. They belonged to a different lineage of large theropods, with long skulls, blade-like teeth, and bodies built for cutting flesh from very large prey. It would be too easy to turn this into a simple image of giants fighting giants. A healthy adult titanosaur may have been a dangerous target, even for a large predator. Predators do not hunt by cinematic fairness. They hunt opportunities. A young sauropod, a sick adult, an animal mired in mud, a carcass found after flood or drought, all would have mattered. The fossil record preserves bite marks and associations in some cases, but it rarely gives us the whole event. We can infer pressure. We cannot choreograph every attack. Still, the scale of the food web is difficult to ignore. A predator the length of a bus moving through a floodplain, where herbivores were larger still. Tracks in mud, broken branches, a carcass drawing scavengers from kilometers away, crocodiliforms near channels, turtles in quieter water, small mammals and lizards in the undergrowth, insects working through dung and decay. A giant dinosaur is the most visible part of the system, but every body around it participates in making that system work. The Huincul Formation, which preserves Argentinosaurus and Maposaurus among many other animals, records a world of braided rivers and floodplain environments in the Nukun Basin. Its vertebrate fauna was rich. Titanosaurs were present, but so were ribachosaurid sauropods, abelisaurids, carcharodontosaurids, noosaurids, turtles, crocodiliforms, fish, and other organisms. Fossil pollen suggests a varied plant community, including ferns, gymnosperms, and flowering plants. This was not an empty stage for one giant animal, it was a crowded ecosystem. Picture the river not as a single blue line, but as a shifting braid of channels, bars, shallow water, mudflats, and dry islands. During wetter periods, channels swell and cut new paths. During drier intervals, water retreats, leaving exposed banks where animals cross. A titanosaur moves through this place slowly. Its feet press into wet sediment. Smaller dinosaurs move along the margins. A predator follows scent or movement. Leaves collect in eddies. Pollen drifts into water and mud, entering the record as grains too small to see with the naked eye, but large enough to tell us what plants were there. Argentinosaurus is often listed among the largest dinosaurs ever found, but its fame rests on incomplete remains. This makes it both impressive and uncertain. The preserved bones are enormous. The reconstructed animal must have been gigantic. But the precise length, mass, and proportions depend on comparison with better-known relatives. Some estimates place it above many other sauropods. Others are more cautious. In a field where a few centimeters of limb circumference can shift a mass estimate by tons, caution is not weakness. It is necessary. The largest dinosaur ever found may never be known with confidence. The fossil record is incomplete in a way that is not evenly distributed. Some animals are known from many individuals, others from one bone. A species represented by a fragment might have been larger than one known from a skeleton, but the fragment cannot answer enough questions. The biggest individual of any species may have died in a place where nothing preserved. The maximum size of dinosaur life may lie outside the fossil record entirely. That uncertainty gives Patagonia's giants a different kind of importance. They do not simply compete for a title. They reveal a range. They show that several Titanosaurs reached truly extraordinary size in the Cretaceous of South America and nearby Gondwanan regions. Patagotitan is important because of its relative completeness and multiple individuals. Dreadnoughtus is important because of its anatomy and growth evidence. Argentinosaurus is important because its fragments show staggering scale. Pseudolonchosaurus is important because it preserves more of a giant body plan in a different part of the sequence. Portosaurus adds another shadow to the group. Known from limited material from southern Patagonia, including enormous vertebrae, it has been placed among the largest sauropods by some estimates. But again, the fossil is fragmentary. The animal is real. The bones are real. The full body remains mostly an inference. In a museum hall, a complete mount gives the illusion of certainty. In the literature, a name may sit beside a length estimate, but behind many of the greatest dinosaurs is a table of missing parts. This is why paleontologists often speak in ranges rather than absolutes. A mass estimate may be expressed with uncertainty. A length may depend on the assumed tail or neck proportions. A dinosaur may be described as among the largest rather than the largest. These words can sound less exciting, but they are more honest. The Cretaceous did not measure its animals for us. It left bones, sediments, minerals, and sometimes traces of skin or eggshell. Science works from what remains. What remains is still enough to be astonishing. A femur 2 meters long does not require exaggeration. A vertebra taller than a child does not need dramatic lighting to matter. A quarry containing more than 100 bones from several gigantic individuals is already extraordinary before any headline calls it the biggest. The story is not diminished by uncertainty. It is deepened by it, because the uncertainty keeps the animals connected to the stone they came from. In the field, there is no thunder when a new bone is found. There is a brush, a notebook, a GPS point, a jacket of plaster and burlap, a careful trench, a decision about where the rock is safest to cut. Discovery is often slow. It is heat, dust, broken tools, meals eaten near trucks, students learning where to place their hands, and the constant awareness that the object under the ground is older than the landscape that now exposes it. The excavation of a giant titanosaur can become an engineering project. A small fossil can be lifted by hand. A sauropod limb bone may require a crew. The bone and surrounding rock must be stabilized, wrapped, turned, moved, loaded, transported, and later prepared. Each step introduces risk. Heavy fossils can crack under their own weight. Roads can be rough. Weather can interrupt work. Logistics do not make the animal less magnificent. They make the science more physical, more grounded in the reality that fossils are objects with mass. The same physicality continues in the museum. A mounted Patagotitan is not a skeleton in the simple sense. It is usually a cast or reconstruction supported by hidden engineering, based on real bones that are too heavy, too fragile, or too precious to place in a dramatic pose. The mount translates the fossil into a body the public can stand beside. It lets people feel scale in a way a paper cannot. But the mount is also an argument, a best reconstruction built from evidence, comparison, and informed choice. Standing beneath such a mount changes the numbers. 37 meters becomes a room. A neck becomes a ceiling. The ribs become a space large enough to walk under. Children look upward. Adults fall quiet. It is not necessary to imagine the animal roaring or charging. Its stillness is enough. The skeleton is a kind of architecture built from anatomy, and it reminds you that land life once found a way to become this large without leaving the ground. The ability to stand and move at that size depended on the limbs. Sauropod legs were columnar, with the major bones arranged to support weight efficiently. The feet were not delicate. They spread force into the ground through padded soft tissues that are rarely preserved but can be inferred from trackways and anatomy. A giant Titanosaurus foot would have been a living compression system, absorbing and distributing mass with every step. The skeleton alone does not tell the whole story. The missing soft tissue mattered. Trackways can sometimes reveal what bones cannot. They show foot placement, stride, herd movement, speed estimates, and the interaction between animal weight and sediment. A track is not a footprint in the casual sense. It is a deformation structure. The surface may preserve the shape of the foot, but deeper layers may record pressure spreading below it. In the case of large sauropods, tracks can show just how much ground responded to their passage. A titanosaur walking across wet floodplain mud would leave more than a mark. Each step pressed down through soft sediment, displacing water, compacting layers, forcing mud around the foot. The animal lifted its limb, and the ground tried to settle back. If a flood came soon enough, new sediment covered the track. If conditions were right, the footprint hardened, was buried, and became part of the rock record. Millions of years later, a track surface could reopen under a different sky. Trackways also remind us that sauropods were not only collections of bones, they were moving animals. They had gait, balance, preferred paths, social spacing, and responses to terrain. Some trackways suggest groups moving in the same direction, others preserve isolated animals. The interpretation of herd behavior from tracks must be cautious, but the evidence makes clear that sauropods used landscapes repeatedly. They crossed river margins, flats, and open ground. They were not static monuments. They traveled. Movement at giant size is slow compared with the quickness of small animals, but it is not helpless. A massive sauropod did not need to sprint to be effective. Its defense lay partly in scale, partly in group presence, partly in the difficulty any predator would face when approaching limbs that could crush or a tail that could strike. A young animal might run. An adult might simply turn, shift weight, or keep moving. In nature, danger is often managed through economy rather than drama. The body produced sound, though we can only approach it indirectly. Breath through a long neck. Feet in mud. Plant stems breaking. Low frequencies that might have carried farther than higher calls. No one can know exactly what Patagotitan sounded like, and the fossil record does not preserve voice in any direct form. But a landscape with animals this large would not have been silent. It would have had deep sounds, repeated sounds, the ordinary noise of mass moving through vegetation. The Cretaceous climate of Patagonia varied by time and place. It was not a single tropical greenhouse painted evenly across the map. Some deposits indicate wetter floodplain conditions. Others show more arid or seasonal settings. The Cerro Barcino Formation itself records changing environments, including alluvial and tufaceous sediments with fossil horizons that have been refined through geochronology. This matters because the giants did not live in an abstract warm world. They lived in specific basins with rivers, ash, soils, droughts, and floods. Volcanic ash is one of the quiet heroes of this story. Ash can bury surfaces, contribute minerals, and provide material that can be dated using radiometric methods. A fossil bone may tell us an animal existed. An ash layer nearby may help place that animal in time. The dates are not always direct. The relationships between layers have to be worked out carefully. But without geology, a dinosaur is only partly understood. The animal belongs to a time, and the time is read through rock. Patagonia's dinosaur record is also tied to the breakup and rearrangement of Gondwana. South America, Africa, Antarctica, Australia, India, and other landmasses had once been connected in different configurations. By the Cretaceous, separations were increasing, seaways were opening, and regional faunas were developing distinct identities. Titanosaurs became widespread, but the southern continents produced their own combinations of herbivores and predators. Patagonia's giants were part of that broader Gondwanan story. Titanosaurs were not restricted to Patagonia. Their fossils have been found on every continent, including Antarctica. They were among the most successful sauropods of the Cretaceous, surviving until the end of the period when many other sauropod groups had declined or disappeared. Their diversity included animals far smaller than Patagotitan, as well as the largest known forms. Some titanosaurs had osteoderms, bony armor embedded in the skin. Others are not known to have had such armor. The group was not one shape repeated. It was an evolutionary radiation. A small titanosaur and a giant titanosaur would have shared a name only in the broad sense that both belonged to the same major lineage. Their lives could have been very different. One might browse at lower levels, move through denser vegetation, and mature at a different size. Another might feed over a wide arc of canopy and river edge plants, crossing open ground with little fear once grown. Evolution does not aim for maximum size. It produces whatever works in a particular place, for a particular body, under particular pressures. The Patagonian giants show that in some places for some titanosaurs, extreme size worked. It worked well enough not once, but repeatedly. The exact evolutionary pathway is still debated. Did the largest titanosaurs inherit a tendency toward gigantism from earlier ancestors and push it further? Did extreme size evolve several times within the group? The answer is not fully settled. But the fossil record of South America suggests that the Cretaceous offered repeated opportunities for enormous herbivores to succeed. Food supply must have been central. A giant herbivore needs enormous amounts of plant matter, but it does not necessarily need highly nutritious food if it can process large volumes efficiently. Sauropods could take in vegetation rapidly and rely on large digestive systems to extract energy. Their size gave them long gut passage times and fermentation capacity. A warm climate and productive river systems could support regrowth. Floodplains create mosaics of vegetation, with young growth along disturbed channels and more established plants in stable areas. This does not mean every Cretaceous floodplain was a paradise. Drought could concentrate animals around shrinking water. Floods could drown individuals or bury carcasses. Seasonal changes could move herds or alter feeding pressure. Large animals are vulnerable to environmental shifts precisely because they need so much. A landscape that supports a giant population in one decade may stress it in another. The fossil record often preserves the moments when animals failed, not the ordinary years when they survived. Death at giant size is also an ecological event. A titanosaur carcass would feed predators, scavengers, insects, microbes, and the soil itself. A large theropod might open the body. Smaller animals would follow. Bones would scatter as tissues decayed, as water moved parts, as trampling or scavenging broke connections. Some bones would be destroyed. Some would be buried. A carcass could remain a landmark for weeks or months, changing as flesh disappeared and the skeleton emerged. After the last soft tissue was gone, the bones still had a journey. Sun could crack them, water could roll them, sediment could cover them, minerals could enter, pressure could flatten or distort them. A femur might remain recognizable. A skull, lighter and more delicate, might vanish completely. This is why many giant sauropods are known from limbs and vertebrae, but not from beautiful, complete skulls. The parts most useful to headlines are not always the parts most likely to survive. Skulls of titanosaurs are rare compared with postcranial bones. The head was small and lightly built. It detached more easily from the body after death. It could be carried away, crushed, or destroyed before burial. This absence affects how we reconstruct feeding behavior and appearance. Teeth can help. Jaw fragments can help. Related species can help. But a missing skull leaves questions that even a massive skeleton cannot answer fully. The face of a giant titanosaur was not monstrous. It was small, almost understated, compared with the body behind it. The nostrils, eyes, jaws, and teeth belonged to a feeding animal, not a creature designed for spectacle. From the front, the head might have looked narrow and practical. From the side, the neck would dominate everything. That contrast between a relatively modest head and an enormous body is one of the reasons sauropods feel so unlike modern land animals. Modern elephants are often used as comparisons for mass, but sauropods were not simply larger elephants. Elephants chew with complex teeth, use trunks, have different limb posture, different reproductive biology, different growth patterns, and a mammalian respiratory system. Giraffes are often used as comparisons for necks, but giraffes have heavy heads, only 7 neck vertebrae, and mammalian constraints sauropods did not share. Comparisons are useful, but they can mislead when pushed too far. The better comparison is often not one living animal, but a set of principles. Large bodies lose heat differently from small bodies. Long necks create mechanical challenges. Hollow bones reduce mass. Efficient respiration helps support active tissue. Herbivores can harvest abundant food if they have the digestive capacity to process it. Predator pressure changes across body size. These principles do not recreate Patagotitan by themselves, but they explain why a body like Patagotitan could exist. The largest titanosaurs were not violations of biology. They were biology operating at an extreme. Every tendon, joint, airspace, muscle scar, and tooth belonged to a functioning organism. Nothing about them was magic. That may be the most astonishing part. They did not float above the ground. They did not escape gravity. They solved gravity, breath, feeding, growth, and movement well enough to live their lives in real landscapes under real skies. For a young titanosaur, the world would have looked very different. Grass did not yet form the sweeping meadows familiar from later ecosystems, and the ground cover would have been a mix of ferns, early flowering plants in some places, horsetails near water, and other low vegetation. The animal's head was closer to the ground. Its danger came from almost every direction. A small theropod might be dangerous. A crocodiliform near water might be dangerous. Even weather could be dangerous. As it grew, the young sauropod would pass through ecological stages. Its diet could shift with height and body size. Its predators would change. Its social relationships might change. A hatchling is not just a small adult, because its role in the ecosystem is different. This is true for many animals today, and it was almost certainly true for titanosaurs. A population of giants includes invisible layers of age, from eggs to juveniles to subadults to massive mature animals. Bone histology gives access to these hidden lives. Thin sections cut from fossil bone can reveal growth patterns, vascularization, pauses in growth, and tissue organization. Under a microscope, a giant dinosaur becomes a record of cellular history. The animal that seems almost geological at full scale turns back into biology at the smallest scale. Growth marks, bone fibers, and remodeling patterns show that these bodies were built through time, not simply assembled at full size. Time was the other ingredient in gigantism. Not just evolutionary time, but individual time. Years of feeding, years of surviving, years of avoiding injury, starvation, disease, floods, droughts, and predators. A full-grown titanosaur was not only large, it was successful. It had passed through the dangerous part of life and reached a size at which the rules changed. Its body was a record of endurance. The Cretaceous of Patagonia was also a world of predators undergoing their own changes. Carcharodontosaurids were dominant large predators during parts of the mid-Cretaceous, but later in the Cretaceous, abelisaurids became especially important in South America. These theropods had short, deep skulls, reduced forelimbs, and distinctive cranial ornamentation in some species. The predator guild was not static across the time of the titanosaurs. The animals hunting, scavenging, or competing around them changed. It is important not to place every famous Patagonian dinosaur in the same scene. Argentinosaurus, Patagotitan, Dreadnoughtus, Phytolonchosaurus, Mapusaurus, and other animals did not all live in one place at one moment. They are separated by geography, formations, and millions of years. A documentary imagination can move between them, but science has to keep the map and the clock visible. Patagonia is not a single Cretaceous habitat. It is a region with many fossil windows. Those windows open onto different ages of giants. In Chubut, Patagotitan's bones point to an early Cretaceous population buried by repeated floods. In Nukun, Argentinosaurus indicates staggering size in a river-dominated ecosystem that also held large predators and many other vertebrates. Near Lake Borealis, Phytolonchosaurus shows a giant body preserved with enough anatomy to teach. Farther south, Dreadnoughtus brings another giant into view, more complete than most, still growing at death. Each locality has its own light, the red and pale beds of one basin, the lake margins of another, the wind-scraped exposures where a bone begins to show, the museum labs where a vertebra is turned slowly under lamps. A map can reduce these places to dots. The fossils restore their weight. They remind us that the dinosaur age did not happen everywhere at once in the same way. It was local. It was sediment by sediment, river by river, animal by animal. The story of Patagonia's giants is also a story of scientific institutions and field knowledge in Argentina. Local researchers, museums, universities, technicians, students, landowners, and field crews have made these discoveries possible. The Museo Paleontologico Egidio Ferruglio in Trelew has been especially central to Patagotitan and to Patagonian paleontology more broadly. Fossils do not simply leave the ground and become science. They pass through communities of work. The public often meets these animals after the hardest parts are finished. A skeleton stands in New York or London. A press image shows a femur beside a person. A news headline announces a new contender for biggest dinosaur. But before that moment are years of excavation, preparation, description, comparison, and debate. Naming a species is not a publicity act. It is a formal scientific claim that has to be supported by anatomy and placed within a broader understanding of related animals. In the case of Patagotitan, the fossils allowed researchers to compare the animal with other giant titanosaurs such as Argentinosaurus, Portosaurus, and Phytolonchosaurus. The differences were not just size differences. They involved anatomical features that could diagnose a new species and clarify relationships among titanosaurs. This is where the story moves away from spectacle. A giant bone is exciting because it is huge. It is scientifically useful because of its shape. A vertebra can reveal where muscles attached, how air spaces invaded the bone, how the column articulated, and how it differs from other taxa. A femur can reveal weight-bearing proportions. A humerus can help estimate mass. A scapula or pelvis can inform posture and movement. These are not decorative details. They are the evidence that turns a large fossil into a known animal. Without them, the story would be only size. Size, however, still matters. It matters because terrestrial life has limits, and these animals approach them. Blue whales can be heavier because water supports their mass. On land, gravity is less forgiving. A sauropod had to stand. It had to get up if it rested. It had to move to food and water. It had to mate. It had to survive injury. Every kilogram was carried through bone and muscle. That is why titanosaurs are among the most extraordinary experiments in the history of life. There is a kind of seriousness in a giant limb bone. It does not invite fantasy as much as calculation. How much force passed through this shaft? How thick was the cartilage at the joint? How much soft tissue surrounded the foot? How did the animal turn? How far could it travel in a day? How much plant matter moved through the gut? The fossil is quiet, but it asks practical questions. The answers are partial, and that partialness keeps the animals alive in scientific imagination. We know enough to reconstruct their world, but not enough to exhaust it. We can place a herd near a river, but not identify every sound it made. We can infer feeding, but not every plant chosen. We can estimate growth, but not the age of every individual. We can see death in the quarry, but not the full sequence of the last day. The most likely everyday life of a giant titanosaur was not constant drama. It was feeding, walking, resting, digesting, avoiding poor ground, finding water, maintaining contact with other individuals, and responding to seasonal change. Predators mattered, but they did not define every moment. A herbivore's life is mostly built around energy. Enough food, enough water, enough safety to continue. The animal's body was a system for turning Cretaceous vegetation into movement and growth. A morning on the floodplain might begin with cooler air over the channels and mist lifting from low places. Small animals move first. Insects on leaves. Crocodiliforms near water. Birds or bird-like theropods in the branches, depending on the time and place. Then, the larger bodies begin to shift. A titanosaur lifts its neck, not dramatically, just enough to bring the head to a new patch of foliage. Another animal steps forward, and mud gives way around the foot. The plants around them were not simply background. They shaped the animals as much as predators did. Tough foliage, seasonal growth, river edge vegetation, young shoots after disturbance, and taller canopy resources all created feeding opportunities. Sauropods with different neck lengths and body proportions could reduce competition by feeding at different heights or in different zones. In ecosystems with multiple sauropod species, resource partitioning may have been essential. The exact diet of Patagotitan is not preserved as a menu. We infer it from teeth, jaw mechanics, plant fossils in its environment, comparisons with related sauropods, and the general structure of the ecosystem. It probably fed on a range of plant material rather than one preferred species. The Cretaceous was a time when flowering plants were diversifying, but gymnosperms and ferns remained important in many habitats. A giant animal likely used abundance rather than selectivity as its basic strategy. Feeding on abundance does not make an animal simple, it makes it enormous in a very particular way. The digestive system becomes a chamber of time, holding plant material long enough for microbes to work. The neck becomes a way of gathering without constantly relocating the body. The limbs become supports for a mobile fermentation system. The tail balances and communicates motion through the rest of the body. The small head is only the beginning of the process. Dung would have mattered. A herd of giant herbivores produces not only footprints and browsed vegetation, but enormous quantities of waste. That waste feeds insects, microbes, and soil processes. It spreads nutrients. It may carry seeds or plant fragments. It changes the ground. The largest dinosaurs were not only consumers of ecosystems, they were ecosystem engineers, moving biomass through their bodies and redistributing it across the landscape. A drought would reveal their dependence. Channels shrink, floodplain pools become crowded, plants near water are stripped heavily. Predators wait closer to the margins. A young sauropod that falls behind becomes vulnerable. A weakened adult may stop in a place where the ground is too soft. The same river system that supports life can become a trap when water retreats or returns too violently. A flood can erase a day in minutes. Rain falls upstream, perhaps far from where the animals stand. Water rises through channels. Mud softens. Carcasses move. Bones separate. Sand and silt cover what remains. The event is destructive for the living, but generous to the fossil record. A burial that is sudden enough can protect bone from long exposure, beginning the slow conversion from remains to evidence. The Patagotitan quarry appears to record multiple flood-related burial events. That repetition is one reason the site is so valuable. It provides several individuals of the same species, not just a single partial skeleton. Multiple individuals help establish which anatomical features are consistent, how much variation exists, and how the animal compares with relatives. A lone fossil can be extraordinary. A sample, even a small one, is stronger. The individuals represented at La Flecha were not necessarily old, fully mature giants at the absolute maximum of their species. Some analyses have described them as young adults. That means the largest Patagotitan individual may have been larger than the known bones suggest. Or it may not. Growth stage matters. A species known from subadult or young adult individuals can be underestimated if the adults were significantly larger. But without the bones, the claim remains uncertain. This is one of the reasons Dreadnoughtus is so intriguing. A gigantic animal, with histological evidence that it was still growing, opens the imagination without giving it permission to invent. It tells us that at least one individual had not reached its final size. It does not tell us exactly how large it would have become. The fossil points forward into an unknown adult body that may never be found. Growth in sauropods involved trade-offs. Rapid growth moves an animal through vulnerable stages, but it demands food and physiological capacity. Large final size offers protection, but it requires years of survival and a landscape that can sustain the body. Egg-laying allows many offspring, but it means limited parental investment compared with many mammals. The strategy is different from an elephant's strategy. It produces many young, knowing that only some will pass through the dangerous filter of early life. The nesting grounds of Titanosaurs in Argentina give this part of the story a physical anchor. Eggshell fragments. Rounded eggs in sediment. Embryonic bones. Skin impressions from animals that never hatched or died before they could grow into the giants their lineage allowed. It is one thing to stand beneath a mounted sauropod and feel small. It is another to look at an egg and realize that the same lineage began life in something so fragile. There is no contradiction between the egg and the giant. They are the same story at different scales. The largest land animals ever known did not begin as large animals. They began as vulnerable embryos, enclosed in shells, dependent on temperature, nest conditions, and luck. The immensity of the adult does not erase the fragility of the beginning. It makes it more visible. Not all titanosaurs nested in the same way, and we cannot assign all nesting evidence to specific named giants. But the broader pattern shows that sauropod reproduction was capable of supporting large populations across landscapes. Nesting sites may have been used repeatedly. Eggs could be laid in clusters. The young may have been independent early, though details remain debated. The fossil record gives strong evidence of reproduction, but limited evidence of behavior. Behavior is the hardest part of these animals to recover. Bones can tell us anatomy. Sediments can tell us environment. Trackways can tell us movement. Eggs can tell us reproduction. But social structure, parental care, communication, and daily choices are harder to reach. Scientists can propose possibilities, but the most responsible reconstructions keep the difference between evidence and inference clear. Even so, the presence of multiple Patagotitan individuals at one site invites questions about social life. Did these animals move in groups? Were they drawn to the same water sources? Did juveniles and adults travel together, or did age classes separate? The quarry cannot answer all of this. It shows repeated presence, repeated death, repeated burial. The living relationships have to be approached indirectly. A group of giant sauropods moving together would change how predators approached the landscape. A lone juvenile might be taken. A cluster of adults creates a wall of bodies. Tails, legs, and sheer mass make the cost of attack high. Predators would read weakness, distance, terrain, and timing. The arms race between predator and prey did not always look like combat. Often it looked like avoidance, assessment, and waiting. The predators themselves left their own evidence: teeth, skull fragments, limb bones, trackways, bite marks in some deposits. A carcharodontosaurid tooth is a different kind of fossil from a sauropod femur. It is smaller, sharper, more direct. It speaks of cutting. The serrations along the edge are not symbolic. They are tools shaped by selection, designed to open flesh in a world where the largest prey could not be swallowed whole or subdued easily. Carcharodontosaurids were major predators in several Gondwanan ecosystems during the early and mid-Cretaceous. In Patagonia, forms such as Titanotitan, Giganotosaurus, and Maposaurus show that large theropods occupied the upper predator roles before abelisaurids became more prominent later. These predators were not ancestors of Tyrannosaurus rex, and they did not belong to the same dominant northern lineage. They represent a separate southern story of apex predation. Maposaurus is known from a bone bed containing multiple individuals, and it lived in the Huincul Formation, the same formation that preserves Argentinosaurus. That does not prove a direct predator-prey event between the two named animals, but it places giant predators and enormous sauropods within the same broad ecosystem. The temptation to stage a battle is obvious. The more useful point is ecological. A landscape supporting giant herbivores also supported predators large enough to exploit them at least as juveniles, weakened adults, or carcasses. The food web of mid-Cretaceous Patagonia may have been one of the most imposing terrestrial systems ever assembled. Not because every animal was huge, but because the upper end of the size range was so extreme. A river basin with Titanosaurs approaching dozens of tons and predators over 10 meters long stretches the imagination. Yet the smaller life remained essential. Without plants, insects, fish, reptiles, small dinosaurs, microbes, and soil processes, the giants could not exist. A fossil leaf can be as important as a limb bone. It tells us what fed the herbivores. A pollen grain can place flowering plants or conifers in the landscape. A turtle shell can show the presence of water. A crocodiliform jaw can place danger near a channel. A burrow can mark soil conditions and small animal behavior. The giant draws the eye, but the ecosystem is built from details. The Cerro Barcino Formation has yielded more than Titanosaurs. Its fossil record includes theropods, sauropods, crocodiliforms, turtles, lepidosaurs, eggshells, footprints, burrows, wood, and other evidence depending on the level and locality. High-resolution work on the formation has improved its time framework, helping researchers understand when different parts of the fauna occurred. This is especially important because a formation can span millions of years. Without dating and stratigraphy, animals can be placed together too easily. In paleontology, time averaging is a constant problem. A rock unit may preserve organisms that lived thousands, hundreds of thousands, or millions of years apart. A list of animals from a formation is not always a living community. Some overlapped. Some may not have. The more precisely a fossil can be placed within the layers, the better we can reconstruct the actual ecosystem. Patagonia's giants require this kind of care because their fame encourages simplification. The refined dates of the Cerro Barcino Formation suggest a mid-Cretaceous Patagonian fauna with strong continuity across certain intervals, but also with details that matter at each locality. Patagotitan comes from the La Flecha area in deposits interpreted within that broader framework. Tyrannotitan and other animals come from related but not always identical horizons. The basin is not a single room, it is a long archive. An archive made of sand, silt, ash, roots, burrows, bones, and flood surfaces. Each layer has its own pace. Some record quiet soil formation. Others record rapid water movement. Some hold scattered fragments. Others preserve articulated or associated material. When paleontologists read these layers, they are not simply asking what lived here. They are asking how the remains entered the ground, how the environment changed, and what the deposit can honestly say. Honesty matters most with the biggest animals because size invites exaggeration. A dinosaur described as the largest ever becomes a symbol almost immediately. Its image spreads faster than the paper can be read. Comparisons multiply. Airplanes, elephants, buses, buildings, these comparisons help people understand scale, but they can also flatten the animal into a spectacle. The real Patagotitan was not a comparison. It was a living herbivore in a specific Cretaceous ecosystem. The same caution applies to the word giant. It can hide differences. Patagotitan and Dreadnoughtus were both Titanosaurs, both enormous, both Patagonian or southern Argentine giants, but they came from different times and places and are known in different ways. Argentinosaurus may have exceeded them in mass, or may not. Phytolancosaurus was another kind of anatomical window. Portosaurus remains a shadow of huge vertebrae. To place them all under one word is useful, but not complete. Still, taken together, they show a continent where sauropod gigantism did not fade quietly after the Jurassic. In the northern hemisphere, the dinosaur faunas most familiar to the public often focus on tyrannosaurs, horned dinosaurs, duckbills, and armored forms. In South America, the Cretaceous record has a different emphasis. Titanosaurs remained central. Abelisaurids and Carcharodontosaurids shaped predator roles. Crocodiliforms diversified in unusual ways. The southern dinosaur world had its own character. This difference reflects geography and history. As continents separated, populations became isolated, and evolutionary paths diverged. South America spent parts of the Cretaceous with distinctive connections and separations from other landmasses. Faunas did not evolve in complete isolation at all times, but they were shaped by barriers, corridors, climate, sea level, and inherited lineages. Patagonia's giants were not random outliers. They were products of southern landmass history. The Andes were not yet the mountain chain we know today. Patagonia's landscapes were affected by basins, volcanic input, shifting rivers, and changing climates. Over tens of millions of years, the region that now feels windswept and open held forests, floodplains, lakes, channels, and nesting grounds. The modern desert is not a failure of memory. It is the surface through which older worlds appear. A person walking those exposures today may see nothing at first. The eye has to learn what bone looks like when it has become stone. The color can be close to the surrounding sediment. The shapes may be broken. A fossil is often recognized by texture, by curve, by a difference in hardness. By the way, weather reveals one surface more cleanly than another. Discovery is partly knowledge and partly attention. Once a giant bone is identified, context becomes urgent. Removing a fossil without recording its position can destroy information. Orientation, depth, association with other bones, sediment type, nearby layers, and evidence of transport or weathering all matter. The Patagotitan quarry was treated like a crime scene in the sense that the position and condition of bones helped researchers interpret death and burial. The animal is not only in the bones, it is in their arrangement. Bones from multiple individuals can become mixed. Water can move smaller elements. Large bones can remain close to where they fell or be shifted by currents. Scavengers can drag pieces. Sediment can slump. Later erosion can remove parts of the original deposit. Interpreting a bone bed requires patience because a single surface may record several processes. The neat living animal is usually not what the quarry preserves. This is why a mounted skeleton is both beautiful and misleading. It restores order to what death and geology scattered. The vertebrae line up. The limbs support the body. The neck extends. The tail balances. visitors see a living shape. Behind that shape is a field record of broken association, missing pieces, comparison with related animals, and the work of reconstruction. The mount is not false. It is a translation. Translation is necessary because no one will ever watch a Patagotitan cross a river. No one will hear the mud around its feet or see water rise around its ankles. The only route back is through evidence: bones, tracks, sediments, eggs, pollen, ash layers, and comparative anatomy. Each is incomplete alone. Together they become strong enough to support a world. The world they support is not silent, but it is restrained. A hot afternoon on the Cretaceous floodplain. The smell of wet soil near a channel. Conifers and flowering shrubs growing in patches. Ferns in low places. Insects moving over leaves. A large herbivore standing with its body angled to the sun. Another animal farther away, partly hidden by vegetation. A predator visible only as movement at the edge of the trees. The Cretaceous was not the Jurassic, and the title of giant dinosaur often pulls Jurassic images into the wrong time. Titanosaurs were sauropods, but the Patagonian giants discussed here lived mostly in the Cretaceous. The Jurassic had its own sauropod icons, such as Diplodocus, Apatosaurus, Brachiosaurus, and others. Patagonia's most famous Titanosaurs show the continuation and transformation of sauropod success after that earlier age, not a simple repeat of it. This distinction matters for the plants, the predators, and the geography. By the Cretaceous, flowering plants were spreading, though their ecological dominance varied by region and time. Predator guilds differed from classic late Jurassic ecosystems. Continents had moved farther apart. Titanosaurs inherited a sauropod body plan with Jurassic roots, but they lived in a changing world. They were ancient in design and current in their own time. In a way, the Cretaceous Titanosaurs are the later chapters of a story that began with smaller sauropodomorphs in the Triassic and expanded through Jurassic giants. They show persistence. Many dinosaur groups changed dramatically across the Mesozoic, but sauropods continued to find ways to remain important large herbivores. Titanosaurs were the last great expression of that success, surviving until the asteroid impact ended the age of non-avian dinosaurs. When that impact came 66 million years ago, Titanosaurs were still alive in some parts of the world. Their lineage did not fade out because it had become obsolete. It was cut off with the rest of the non-avian dinosaurs in a global catastrophe. The animals of Patagonia's giant age did not know they were late in the story. They lived in the middle of their own present, feeding, growing, nesting, and dying under skies that seemed stable enough. Extinction gives the story its boundary, but it should not dominate everything before it. For most of their history, Titanosaurs were not doomed creatures. They were successful. They dispersed widely. They diversified. They occupied ecosystems across continents. In Patagonia, some reached sizes that still challenge our methods of reconstruction. To see them only through their ending is to miss the long success that came before. That success included smaller titanosaurs as well. Saltosaurus, from later Cretaceous rocks of Argentina, though not from the same giant-focused context, was much smaller than Patagotitan and is famous for evidence of bony armor in the skin. Its existence reminds us that Titanosauria included many strategies. Gigantism was spectacular, but it was not the only solution. Evolution does not crown a single ideal form. It produces diversity. Armor in some titanosaurs raises interesting questions about predator pressure, display, physiology, and inherited traits, but it should not be generalized to all giants. Some titanosaurs had osteoderms. Many are not known to have them. The fossil record of skin and armor is incomplete, and absence of evidence is not always evidence of absence. But where osteoderms are found, they add another layer to how varied these animals could be. The idea of a giant sauropod with armor seems almost excessive, but nature often combines traits in ways that surprise us. A body can be massive and still carry defensive structures. A lineage can produce both giants and dwarfs. An animal can look slow and still be ecologically powerful. The more fossils Patagonia yields, the less the Titanosaurs look like a single type of dinosaur, and the more they look like a broad experiment in living large, and sometimes not so large, at the end of the Mesozoic. The landscape also held animals that did not dominate headlines. Turtles moved through water and onto banks. Crocodiliforms, some unlike any modern crocodile, filled both aquatic and terrestrial roles. Small theropods hunted insects, lizards, and mammals. Pterosaurs crossed the sky. Early birds or bird-like dinosaurs occupied parts of the air and vegetation, depending on the time and place. The giants lived among them, not above them in any absolute sense. A useful way to think about a titanosaur ecosystem is as a flow of energy. Sunlight becomes plant tissue. Plant tissue becomes sauropod mass, smaller herbivore mass, insect bodies, microbial communities, and soil carbon. Predators and scavengers draw from those herbivores. Decomposers return material to the ground. Rivers move nutrients, sediment, and bodies. Floods reset parts of the landscape. Volcanic ash adds minerals and time markers. The giant is one node in that network, even if it is the most visible. This network would have changed with seasons. In wetter times, vegetation expands and channels connect. Animals spread out. Nesting may occur in suitable places. In drier times, movement becomes more focused around reliable water. Tracks overlap. Dung accumulates. Predators find predictable paths. Bones of animals that die near water have a better chance of entering the sedimentary record. The fossil record may be biased toward stress, because stress brings bodies together. A waterhole during a dry interval would not be peaceful simply because the animals were herbivores. Large bodies require space. Juveniles have to avoid being jostled or separated. Predators watch edges. Crocodiliforms wait near mud and water. The ground becomes churned by feet. Disease can spread where animals gather. A landscape that supports giants also tests them. Then rain returns. Channels run brown. Footprints soften. Plants respond. New growth appears on disturbed banks. The same place that held danger becomes productive again. Dinosaurs return not because they understand cycles in the abstract, but because bodies follow water and food. Over years, over generations, these movements become part of the pattern recorded in tracks, bones, and sediment. Fossil sites rarely preserve continuous behavior, but they can preserve repeated use of landscapes. Track surfaces show paths. Bone beds show mortality. Nesting grounds show reproduction. Sedimentary structures show water flow and floodplain stability. Pollen and plant fossils show vegetation. Each type of evidence speaks in a different way. The task is to combine them without forcing them to say more than they can. That is especially important when reconstructing herds. Multiple individuals at one quarry do not automatically mean a social herd died together. Trackways moving in the same direction may indicate group movement, but they can also record repeated use of a path. Nesting grounds can show repeated reproductive behavior, but not necessarily parental care. The safest language often sounds modest. The evidence suggests. It may have. It is possible. These phrases protect the past from our desire to make it too certain. Even with modest language, the images remain powerful. A line of sauropod tracks crossing a surface. A nest horizon filled with eggshell. A femur emerging from a hill. A vertebra so large that its air spaces look like rooms. A quarry where multiple giants entered the ground across repeated floods. These are not dramatic because we exaggerate them. They are dramatic because they exist. The desert today adds its own atmosphere. Patagonia is windy in a way that feels almost constant. Dust moves over the ground. Low plants bend. The sky can seem too large. In that openness, A fossil bone does not appear as a relic from a crowded forest or floodplain until you understand the rock around it. The modern emptiness makes the ancient abundance feel stranger. The transformation from Cretaceous floodplain to modern outcrop involved tens of millions of years of burial, mineralization, uplift, erosion, and climate change. Sediments that once lay under rivers became rock. Rock that once lay buried rose and was cut by weather. The bones inside did not wait in the sense a living thing waits. They simply persisted. Minerals replaced or filled spaces. Weight compressed layers. Time changed everything around them. When a fossil is exposed, the process becomes urgent again. Exposure is discovery, but it is also danger. Weathering can destroy bone after millions of years of protection. A fossil that has survived deep time can crumble in decades or years at the surface. That is why fieldwork often feels like rescue. The bone is not just found, it is caught at the brief moment between burial and loss. This brief moment connects the living animal to modern science. A ranch worker notices a bone. Paleontologists arrive. The quarry expands. Years of field seasons follow. Fossils are moved to labs. Papers are written. Reconstructions are built. A dinosaur receives a name. Then, the public meets it as an icon, often forgetting how narrow the path was between remaining hidden and being destroyed by weather. Patagotitan's public mount has traveled far beyond the ranch where the fossils were found. Casts and reconstructions allow a dinosaur from Chubut to stand in major museums, introducing millions of people to Patagonian paleontology. The real bones remain scientific objects, but the mounted skeleton becomes a cultural one. It carries the animal into public imagination, where size is the first lesson and uncertainty is often the second. Museum mounts also change as science changes. A posture can be updated. A mass estimate can be revised. A species once claimed as the largest may later be described more cautiously. This is not a problem with paleontology. It is one of its strengths. The past is fixed, but our understanding of it is not. Every new fossil, every new method, every reanalysis can adjust the picture. The picture that remains is still immense. Patagotitan may not be definitively larger than every other dinosaur. Argentinosaurus may or may not outweigh it. Dreadnoughtus may have been lighter than first estimated. Portosaurus may remain too incomplete for confidence. But the group as a whole stands near the upper edge of what terrestrial vertebrate life has achieved. The exact ranking matters less than the range of possibility they reveal. There is a humility in that. The largest animal ever to walk on land may be known only from fragments, or may not have been found, or may have eroded away before anyone could see it. The fossil record gives us enough to know that giants lived, but not enough to close every question. The missing bones are part of the story, not an inconvenience outside it. Paleontologists sometimes use equations based on limb bone circumference because the limbs carry weight. They also use volumetric models, where a reconstructed body is given a plausible amount of soft tissue and density. Both approaches can be useful, and both can disagree. A wider torso, a deeper chest, a more muscular tail, or a different neck posture can shift mass estimates. For giant animals, small proportional changes become large numerical differences. This is why a single mass estimate should never be treated as the animal itself. A number like 60 tons is an interpretation, not a fossil. It is based on methods, comparisons, and assumptions that can be tested and revised. The fossil is the femur, the vertebra, the rib, the quarry position, the histology, the surrounding sediment. The number helps us think about the animal, but it does not replace the evidence. Still, humans need scale. We understand by comparison. A femur as tall as a person, a body heavier than many elephants, a neck longer than a truck, a skeleton that barely fits inside a hall. These comparisons are imperfect, but they let the mind approach something outside ordinary experience. The trick is to use them as doorways rather than endpoints. Beyond the doorway is an animal that lived under constraints. It had joints that wore, muscles that fatigued, skin that healed or scarred, a gut that filled and emptied, parasites perhaps, infections perhaps, injuries perhaps. Fossils can sometimes preserve evidence of disease or trauma, though not always for these particular giants. A huge animal is still an animal. It is not immune to biology. A scar on bone, when present, can make the past feel closer than a perfect skeleton. It shows that the animal endured something. A healed fracture, a bite mark, a growth abnormality, an infection. Such traces are not necessary for wonder, but they change its texture. The animal becomes less like a species illustration and more like an individual body that had a history. For many giant titanosaurs, individual life histories remain difficult to reconstruct because the material is incomplete or represents multiple animals. But age, growth, and death can sometimes be approached through bone microstructure and quarry context. In Patagotitan, research included questions about age and possible death circumstances. In Dreadnoughtus, histology suggested continued growth. These are not side notes. They are evidence that giants had life stages, not just adult silhouettes. The adult silhouette, though, is unavoidable. A titanosaur seen from the side is a line of improbable proportions. Head, neck, torso, tail, all extended across more space than any modern land animal. The back may not be as high as the neck implies, but the overall length dominates the scene. The animal occupies the landscape horizontally as much as vertically. It is not just tall, it is long enough to be a moving boundary. In vegetation, the body would appear in pieces. A neck above foliage, a shoulder moving behind trunks, a tail crossing an open gap. The whole animal might be difficult to see at once unless it stepped into open ground. This is easy to forget in museum halls, where the skeleton is isolated and complete. In life, the giant was embedded in plants, dust, water, light, and distance. Distance also shapes how we understand their social presence. Large animals today often communicate over distance through low-frequency sound, scent, visual posture, and repeated pathways. Titanosaurs may have used some comparable methods, though the specifics are uncertain. Their size would allow visual recognition across open ground. Their movements could create tracks and trails. Their bodies could influence where other animals moved simply by occupying space. We should not assume complex herd behavior identical to elephants, nor should we assume solitary indifference. The evidence is not enough for that. Sauropods may have varied widely in social behavior across species and ages. Some trackways suggest group movement. Bone beds suggest repeated aggregation or mortality. Nesting grounds suggest reproductive concentrations. The safest reconstruction allows social possibilities without assigning modern mammal patterns too confidently. A group of titanosaurs near a river might not behave like an elephant herd, but it would still create relationships. Individuals keep spacing. Young animals stay near cover or near larger bodies. Adults move toward food and water. If one animal reacts to a predator, others may respond. Sociality can be simple and still effective. It does not need to be human-like or elephant-like to matter. The predators reading those movements had their own intelligence, senses, and limitations. A Carcharodontosaurid did not need to defeat an adult titanosaur in a direct contest to benefit from living near giants. Juveniles, eggs, carcasses, and weakened animals provided resources. A predator could follow herds, patrol river crossings, scavenge after flood deaths, or target smaller herbivores in the same environment. The presence of giants reshaped predator opportunity. A carcass after a flood would draw the world inward. Large theropods first, perhaps, smaller scavengers later. Insects almost immediately. Crocodiliforms if water remained nearby. Bones exposed, shifted, broken, covered. The smell would be intense, but the fossil record has no odor. It keeps the aftermath in mineral form, stripped of sound and heat, leaving only enough to suggest what happened. This stripping away is why paleoecology requires multiple lines of evidence. A bone bed alone may not reveal season, climate, or cause of death. Sedimentology can indicate flood or channel conditions. Plant fossils can suggest habitat. Isotopes may give clues to diet or environment in some cases. Trackways can show movement. Together, they help reconstruct the conditions under which giant titanosaurs lived and died. The popular desire for certainty often clashes with the fragmentary nature of deep time. People want the biggest dinosaur, the exact weight, the precise speed, the definitive predator, the final answer. Paleontology can answer some questions strongly and others only in ranges. The best reconstructions are not vague because scientists lack imagination. They are cautious because the evidence deserves respect. Respect does not make the giants smaller, it makes them real. A real Patagotitan is more interesting than an inflated one. A real Argentinosaurus, known from immense fragments and careful comparison, is more compelling than a fantasy skeleton. A real Dreadnoughtus, enormous and still growing, is more powerful than a fixed number on a chart. The bones do not need us to make them bigger. They were already big enough. To understand why titanosaurs could reach such size, it helps to return to the whole sauropod inheritance. The long neck reduced the need to move the entire body while feeding. The small head reduced mechanical load. The air sac system reduced skeletal mass and supported efficient respiration. The columnar limbs supported weight. The digestive system processed large volumes of plant material. Egg laying allowed reproduction at large adult size without the constraints of carrying a gigantic fetus internally. No single trait explains everything. Together, they opened a path. Environment then determined where that path could lead. Warm climates, productive vegetation, broad floodplains, and stable enough ecosystems allowed giant herbivores to maintain populations. Isolation and regional evolution shaped which lineages expanded. Predators created pressure, but size reduced adult vulnerability. Growth rates moved juveniles towards safer body sizes. The result was not inevitable. It was contingent, built from inherited anatomy and Cretaceous opportunity. Patagonia may have been one of the places where opportunity and inheritance met repeatedly. Its basins preserved the evidence, but preservation alone does not create giants. The animals had to live there first. They had to feed there, reproduce there, die there, and enter sediment. The abundance of discoveries tells us about geology and fieldwork, but it also points toward real biological success in the ancient ecosystems of southern South America. Think of the same landscape across generations. A river shifts east. A flood buries a carcass. Plants grow over the new surface. Years later, another group of titanosaurs passes. A juvenile dies near a channel. More sediment arrives. Ash falls in the distance and is washed into the basin. Time stacks these moments. None of the animals know they are becoming a formation. They are simply living on a floodplain that will one day be cut open by erosion. Erosion is slow, but it is not gentle. It removes mountains, opens basins, exposes bones, and destroys them. Patagonia's wind, rain, and temperature changes work constantly on the rock. A fossil that appears at the surface is already entering a final phase unless someone finds it. The same forces that reveal the past also take it apart. This is why fossil collecting must be done responsibly and legally. Dinosaur bones are scientific heritage, not just objects. Their value depends on context, documentation, preparation, and access for study. A giant bone removed without data loses much of what it could teach. Patagonia's major discoveries are not just trophies of size, they are research specimens tied to formations, localities, and field records. In the case of Patagotitan, the number of bones and individuals allowed researchers to build a more complete anatomical picture than is possible for many other giant titanosaurs. The skeletons were not complete, but they were informative. The material included major limb bones and vertebrae, enough to estimate mass, compare anatomy, and reconstruct a public mount. The result was a rare combination of scale and evidence. That combination is why Patagotitan captured public attention. It is not the only contender for the largest dinosaur, but it is one of the most visible. The skeleton extends through museum space with a kind of quiet insistence. It does not need a chase scene. The body is the scene. Viewers stand beneath it and understand, physically, that the history of life includes forms no modern land animal approaches, yet the animal itself lived without knowing it was exceptional. It did not know it was one of the biggest. It did not know Patagonia. It did not know Cretaceous. It knew hunger, water, heat, bodily pressure, the presence of other animals, the feel of ground beneath its feet. The categories are ours. The life was its own. Scientific names, periods, formations, and estimates are human tools for ordering that life after the fact. They matter because they let us compare, test, and communicate. But they are not what the animal experienced. Patagotitan majorum is a name attached to fossils from a place and time. The living population was a set of bodies moving through an environment that no longer exists. The same is true for Argentinosaurus huinculensis. The name points to Argentina and the Huincul area, to a set of fossil remains that have become central to discussions of maximum dinosaur size. But the living animal was not an entry in a size chart. It was a herbivore using a riverine landscape, one of many organisms in a rich ecosystem. Its greatness in our eyes comes from scale, but its success came from ordinary survival repeated day after day. Ordinary survival at that size is not ordinary from our perspective. Every day requires enough food to maintain the body, enough water to sustain it, enough stability in the limbs to move without catastrophic injury, enough sensory awareness to respond to terrain and other animals. A fall for a giant can be serious. Bad ground can matter. Infection can matter. The body is powerful, but it is also vulnerable to its own scale. Some paleontologists have debated whether the very largest sauropods were near the maximum possible size for land animals. The answer depends on many variables: bone strength, muscle power, metabolism, reproduction, food supply, heat balance, and ecological pressure. Titanosaurs did not necessarily reach a hard absolute limit, but they approached a region of biology where every additional increase in size carries major costs. That is what makes their existence scientifically important. They stand at the edge of possibility, but not beyond it. The fossils show that possibility was real. Their bones are not thought experiments. Their footprints, where preserved, are not abstractions. Their eggs, relatives, predators, and floodplains place them in a working world. They were immense, but they were not impossible. A bone in the desert is enough to prove that. The biggest dinosaurs ever found are not only a list of names, they are a set of problems. How do you estimate a missing body from partial remains? How do you support a neck that long? How do you grow from a small egg to a multi-ton adult? How do you gather enough food? How do ecosystems support multiple giant herbivores? How do predators interact with prey too large to attack directly? How does a carcass become a fossil? Patagonia helps answer each of these questions, though never completely. The answers also change with new discoveries. A newly described titanosaur may add anatomical information without becoming the largest. A reanalysis may lower or raise mass estimates for famous taxa. Improved dating can shift a fossil into a more precise time interval. New fieldwork can show that animals once thought to be contemporaries were separated by millions of years. The field remains active, and Patagonia continues to produce material that reshapes the story. Recent finds such as Chucarasaurus from Rio Negro remind us that the record is still growing. Not every new giant rewrites the top of the size chart, but each one adds anatomy, geography, and evolutionary context. A femur, humerus, or vertebra from a new species can help clarify how titanosaurs diversified, how their limbs handled stress, and how body size varied across lineages. The story is not closed. Popular attention often goes to the largest number, but paleontologists may be more excited by completeness, age, or unusual anatomy. A smaller skeleton can answer more than a giant fragment. A modest species can reveal relationships. A juvenile can illuminate growth. A nesting site can transform understanding of reproduction. Size is a powerful entrance into the subject, but it is not the only reason these fossils matter. Still, size is where many people begin. A child sees a skeleton that reaches across a hall and feels wonder before knowing any taxonomy. That wonder is not shallow. It is the first contact with scale, and scale is a real scientific fact. The task is to guide that wonder toward evidence, to let the enormous body lead into questions about anatomy, environment, evolution, and time. Time is the final scale. A Patagotitan bone lay in the ground for roughly 100 million years before modern eyes recognized it. Human civilization is only a thin surface at the end of that span. The ranch, the museum, the road, the tools, the names, all belong to the last instant of the fossil's history. The animal lived and died long before any of them existed. During those 100 million years, continents shifted. The Atlantic widened. The Andes rose toward their modern form. Climates changed. Mammals diversified after the extinction of non-avian dinosaurs. Grasslands spread. Ice ages came and went. Humans appeared. Languages formed. Someone eventually walked across a Patagonian ranch and noticed that a pale curve in the ground was not ordinary stone. That is the strange intimacy of paleontology. Deep time becomes close through contact. A hand brushes dust from a fossil. A scientist measures a bone. A child stands beneath a cast. The animal remains unreachable, but the evidence is near enough to touch. The distance is immense, and the connection is physical. The physical connection must be handled with discipline. The script of a lost world is not written in a single fossil. It is assembled from many sources, each with limits. Patagotitan tells us about one giant from Chubut. Argentinosaurus tells us about another from Nukon. Dreadnoughtus tells us about a southern Patagonian giant with unusual completeness. Futuloncosaurus fills in anatomy from Lake Borealis. The formations tell us about environment. Together, they support a broader picture of Patagonian Titanosaur success. But the picture remains open. Future discoveries could change rankings, relationships, and reconstructions. A more complete Argentinosaurus could clarify its proportions. New Patagotitan material could adjust growth interpretations. Additional Dreadnoughtus specimens could show adult size. New dating could refine the timing of faunal changes. Paleontology is not finished with these animals. It has only begun to understand them. The unfinished quality is part of the appeal. A giant vertebra on a table is both answer and question. It answers whether such animals existed. It asks how they lived. It answers that a certain lineage reached enormous size. It asks what ecological conditions allowed it. It answers with bone. It asks for the rest of the body, the rest of the landscape, the rest of the life. We will never have all of it. No fossil record gives back a complete world. Colors are mostly gone. Sounds are gone. Most behavior is gone. The exact pattern of a herd moving through morning light is gone. But enough remains to build a careful reconstruction, and careful does not mean cold. The past becomes more moving when it is treated as real. A real Cretaceous floodplain was not arranged for our understanding. It was messy. Channels shifted. Bodies decayed. Bones broke. Species overlapped unevenly. Populations rose and fell. Weather changed the rules. The fossils we find are fragments from that complexity, filtered by preservation and discovery. The giants of Patagonia emerge from this mess, not from a clean myth. That is why the most useful narrative follows evidence back into place. Start with the bone, then the quarry, then the formation, then the animal, then the body plan, then the ecosystem, then the broader lineage. Then return to the bone, because the bone is the reason we can speak at all. Without it, the giants would remain only possibilities. The bone tells us that an animal of almost unimaginable scale once moved through Patagonia, not in legend, not in speculation, in muscle and blood and breath. It fed on plants that grew from Cretaceous soils. It left weight in the ground. It carried air through its bones. It grew from an egg. It lived among predators, rivers, floods, and other dinosaurs. It died, and part of it remained. Part of it remained long enough for us. The biggest dinosaurs ever found are sometimes described as if they were endpoints, but they are better understood as intersections. Biology meets geology. Evolution meets climate. Public wonder meets careful measurement. A ranch discovery meets a museum laboratory. A femur meets an equation. A floodplain meets a fossil haul. Each intersection adds something. None of them alone is the whole story. When the title says Giants of Patagonia, it does not mean one winner. It means a region where the evidence for terrestrial gigantism is unusually rich and unusually important. It means Patagotitan at La Flecha. It means Argentinosaurus from the Huincul Formation. It means Dreadnoughtus in southern Patagonia. It means Futalancsaurus from Nukon. It means fragmentary giants like Portosaurus. It means the surrounding ecosystems that made them possible. It also means the question of why so many of the largest names come from this part of the world. Part of the answer is preservation and exposure. Part of it is the history of fieldwork. Part of it is the Cretaceous success of Titanosaurs in Gondwana. Part of it may be environmental productivity, body size evolution, and regional ecology. No single explanation is enough, because the pattern itself is made from several processes. In the end, the largest dinosaurs do not ask us only to imagine height or mass. They ask us to imagine duration. A lineage of sauropods beginning long before Patagotitan. A young animal growing, year by year. A floodplain accumulating layer after layer. A bone buried and mineralized. A continent moving. A desert forming. A fossil appearing. A human noticing. The giant is not just large in space, it is large in time. That scale can make human life feel small, but not meaningless. The opposite is true. We are brief enough that finding these bones is remarkable. A species that has existed for only a moment has learned to read animals buried for 100 million years. We can misread them, we can overstate them, but we can also correct ourselves, measure again, compare again, and bring the lost world closer without pretending to possess it completely. The work continues because the rocks continue to hold material. New exposures open. Old collections are re-examined. CT scans reveal internal structures. Histology reveals growth. Stratigraphy refines time. Digital models test posture and mass. Collaboration expands access. Patagonia's dinosaurs are not just 19th century trophies or static museum icons. They are active scientific subjects. Even a mounted skeleton is not static if you know how to look at it. The neck carries questions about air sacs and posture. The limbs carry questions about mass and movement. The ribs imply lungs, organs, and a digestive system large enough to process mountains of vegetation across a lifetime. The tail balances the body and completes the length. The small head reminds you how unusual sauropod engineering was. Every part is an argument shaped like an animal. The anatomy of a titanosaur pelvis rarely attracts the same attention as the neck, but it carried much of the body's meaning. The pelvis anchored the hind limbs, supported the base of the tail, and helped transmit enormous forces through the body as the animal walked. In a giant sauropod, even a slow step involves load transfer on a scale that no living land animal can reproduce. The bones had to be broad, reinforced, and integrated with muscles that left their signs on the fossil surfaces. A pelvis is not visually graceful in the way a long neck is, but it is one of the places where gigantism becomes practical. The tail, too, was more than an extension trailing behind the animal. It balanced the neck and torso, influenced turning, and carried muscles that helped move the hind limbs. In many sauropods, the tail narrowed into a long tapering structure, but in Titanosaurs the details varied. Caudal vertebrae can be important for identifying relationships because their shapes differ between groups. A single tailbone may not look dramatic to a visitor, but to a paleontologist it can carry signals of ancestry, function, and body posture. The shoulder girdle carried its own burden. The forelimbs of Titanosaurs supported the front of a massive body, and their bones can be crucial for mass estimates. The humerus, like the femur, is one of the great weight-bearing elements. Measuring its circumference is one way to approach body mass, because living animals and extinct animals both have to obey the relationship between limb strength and load. The equation is not perfect, but it begins with a simple fact. Weight leaves evidence in the bones that carried it. The feet remain harder to reconstruct than the major limb bones. Fossilized foot bones preserve the skeleton, but the living foot included cartilage, pads, ligaments, skin, and other soft tissues that rarely fossilize. Trackways help fill in the missing anatomy. They show the shape of the weight-bearing surface, the width of the stance, and sometimes the presence or absence of claw impressions. In sauropods, the front feet and back feet did not function identically. The body was a four-limbed bridge, but each end of that bridge carried weight in a different way. A titanosaur walking over firm ground may have left little lasting sign. The same animal crossing saturated mud could press a track deep enough to alter layers below the surface. Tracks can also be distorted by the mud's behavior, by slipping, by later sediment collapse, or by erosion before burial. Reading them is not as simple as looking at a footprint. It is closer to reading a physical experiment conducted by a living animal and preserved by accident. The skin of these animals is mostly absent from the record, though rare impressions from titanosaurs and embryos give hints of texture. Sauropod skin was not smooth like a whale's skin, and it was not feathered like many theropods. It likely carried scales or pebbly textures, varying across parts of the body. In armored titanosaurs, osteoderms added hard elements within the skin. In the great Patagonian giants, where skin is not directly known, reconstructions must lean on relatives and caution rather than certainty. Color is even further from reach. A Patagotitan may have been gray, brown, patterned, countershaded, dust-covered, or something else entirely. Large modern animals often have muted colors, but that is not a rule that can simply be placed over the Cretaceous. Display, camouflage, heat, habitat, and inheritance all shape color. Fossils rarely preserve pigments in large dinosaur skin. The safest reconstruction keeps color modest, unless evidence says otherwise, but the living animal would not have been a museum-gray skeleton. It had skin under sunlight. Heat balance would have been a constant issue. Large animals lose heat slowly because surface area increases more slowly than volume. In a warm Cretaceous climate, a giant titanosaur may have faced the challenge of avoiding overheating, especially during activity or in open landscapes. Behavior could help. Feeding at cooler times, resting in shade, using water margins, orienting the body, and relying on blood flow through large surfaces may all have mattered. The animal's physiology is not fully known, but its size alone makes heat part of the story. Cold nights, where they occurred, would have created the opposite advantage. A giant body cools slowly. The same mass that risks overheating in the afternoon can buffer the animal when temperatures fall. This thermal inertia is one reason large bodies can be advantageous in certain climates. It does not mean titanosaurs were sluggish or simple. It means their physical relationship with the environment was different from that of a small mammal, a small theropod, or a hatchling sauropod moving through the same night air. The respiratory system helped with more than oxygen. Air sacs in dinosaurs may also have assisted with heat exchange, though the details in sauropods remain studied and debated. In birds, Air sacs and one-way airflow through the lungs create highly efficient breathing. Sauropods inherited parts of this system within Saurischian dinosaurs, and their pneumatic vertebrae preserve evidence of air spaces. These spaces are among the most important anatomical clues to how a neck and torso could reach such size without becoming impossibly heavy. A giant vertebra is a good place to see this engineering. The outside can be enormous, but the inside is not a solid mass. Laminae, fossae, chambers, struts, and openings create a structure that places bone where it is needed and removes it where it would only add weight. The result is not fragile in the ordinary sense. It is efficient. A bridge is not weaker because it is not a solid block of steel. It is stronger because its material is placed according to load. This architecture also complicates fossilization and preparation. Thin walls, internal cavities, and delicate surfaces can be damaged by pressure, erosion, or tools. A vertebra that looks like a massive object may contain fragile partitions. Preparing it requires understanding the structure before it is fully visible. The preparator has to anticipate hollows, cracks, and surfaces hidden beneath rock. In this way, the anatomy of the living animal continues to shape the labor of modern science. There is a quiet intimacy in preparation work. The animal is gone beyond recall, yet a person may spend weeks revealing the curve of one process, the edge of one articulation, the texture of one scar where muscle or ligament once attached. The work is repetitive, patient, and precise. It does not resemble the dramatic moment of discovery, but it is where much of the animal actually becomes knowable. A prepared fossil still has to be compared. Paleontology is a comparative science because no fossil explains itself alone. A bone's identity depends on its relationships to other bones, other species, other formations, and other interpretations. The same surface that looks unique at first may turn out to be common in a clade. A difference that appears minor may become diagnostic. Patagotitan, like every named dinosaur, exists scientifically because its fossils could be distinguished from those of other animals in a consistent anatomical way. This comparison becomes difficult when many relatives are fragmentary. Giant titanosaurs often preserve overlapping parts poorly. One taxon may be known from vertebrae, another from limb bones, another from pelvis and tail. Comparing them can be like comparing incomplete sentences from the same lost language. The meaning is there, but the missing words matter. This is why new discoveries can change relationships among animals that have been named for decades. The desire to rank the giants can sometimes obscure the need to revise them. Argentinosaurus, Portosaurus, Patagotitan, Dreadnoughtus, Phytoloncosaurus, and other giant titanosaurs have all been placed into different discussions about size, anatomy, and relationships. Some are better constrained than others. Some may be close relatives. Some may represent separate experiments in extreme body size. The exact tree matters because it tells us whether gigantism evolved once, several times, or through repeated enlargement within related branches. If extreme gigantism evolved more than once within Titanosauria, then the Cretaceous world repeatedly opened similar pathways. If it evolved mainly within one branch, then a particular inherited anatomy may have been especially important. The evidence has been interpreted in different ways, and new material continues to matter. The largest dinosaurs are not only large bodies, they are data points in a broader evolutionary question about how often life can approach the same extreme. The answer may not be clean, because evolution itself is not clean. Body size changes gradually in some lineages, rapidly in others, and can reverse when environments change. Island settings can produce dwarfing. Productive continental settings can allow enlargement. Predators, climate, food quality, reproductive strategies, and inherited anatomy all interact. A titanosaur lineage does not decide to become giant. Populations shift over generations as survival and reproduction favor certain bodies under certain conditions. The result, when viewed from millions of years away, can look like inevitability. It was not. A flood kills one group and preserves them. Another population leaves no fossils. A climate interval supports high productivity. A lineage happens to have the right anatomy. A basin happens to preserve the bones. A modern landscape happens to expose them. The giants we know are the survivors of life and the survivors of preservation, two filters stacked across deep time. There were probably other giants we will never name. A land animal can live, reproduce, and die without leaving a single fossil that reaches us. Even in fossil-rich regions, preservation is selective. Bones on uplands may weather away. Bodies in acidic soils may dissolve. Carcasses far from sediment may be scattered and destroyed. The true diversity of giant titanosaurs was almost certainly greater than the named record. The named record is the part that reached the surface in a readable form. This should make us cautious when discussing the biggest dinosaur ever found. It should also make us grateful for the animals we do have. Patagotitan is not just famous because it is enormous. It is famous because it is enormous and comparatively well represented. Dreadnoughtus is not just important because of its mass. It is important because its skeleton gives a rare view of body proportions. Phytolonchosaurus matters because it preserves a neck and torso that can be studied in detail. Each fossil answers a different part of the same larger question. The question extends into locomotion. How fast could these animals move? The safest answer is slowly compared with smaller dinosaurs, but not immobile. Trackway studies of sauropods generally suggest walking speeds rather than running speeds. At extreme size, running in the sense of an aerial phase, with all feet off the ground, would be mechanically unlikely. But walking can still cover distance. A large animal moving steadily for hours can cross a landscape effectively without ever appearing quick. Turning would have required space. The long body, wide stance, and tail would make sharp turns costly. Paths through vegetation might be shaped by repeated movement. River crossings would have to be chosen carefully because soft ground could be dangerous. A titanosaur did not need roads, but it likely used familiar routes where terrain and water allowed passage. In this way, the animals could create trails that other organisms used, altering the movement patterns of the ecosystem. Their feeding could also open habitats. Browsing by giant herbivores may have broken branches, reduced certain plants, promoted regrowth, and created gaps. Modern elephants alter forests through feeding and movement. Sauropods were not elephants, but the principle that very large herbivores shape vegetation is likely. A herd of titanosaurs could change plant structure along river margins simply by repeated use. Their bodies were not only present in the landscape, they were forces acting on it. In a dry season, those forces would concentrate. The same trails lead to water. The same banks are trampled. The same plants are browsed heavily. Dung accumulates, attracting insects and small scavengers. Predators learn where vulnerable animals pass. Floodplain life becomes compressed around what remains of the river. Then, when rains return, sediment can cover tracks, bones, dung, leaves, and shells, turning a season of stress into a layer of evidence. The fossil record is biased towards such moments of concentration and burial. It may tell us more about water margins than uplands, more about flood deaths than quiet deaths, more about animals that lived near sediment than those that stayed away from depositional areas. This means our picture of titanosaurs may overrepresent certain environments. Giants certainly used floodplains, but they may also have used habitats that rarely fossilized. The animals were larger than the record that holds them. The same bias affects predators. Large theropod teeth preserve more readily than delicate skeletons. A tooth lost while feeding may enter sediment even if the predator's body never does. This can make predators appear through isolated signs rather than full animals. A serrated tooth in a deposit may suggest presence, but it cannot by itself reveal abundance, behavior, or exact prey choice. The ecosystem has to be reconstructed from uneven pieces. There is a particular fascination in isolated teeth. They are small compared with sauropod bones, but they carry direct evidence of feeding ecology. Their shape, serration density, curvature, wear, and breakage can suggest how they functioned. In Patagonia's Cretaceous ecosystems, large theropod teeth remind us that the giants lived under observation by animals built to cut meat. Even if adult titanosaurs were rarely attacked, their world was not safe. Safety is always relative in nature. An adult titanosaur may have been protected from most predation, but not from drought, disease, injury, flood, or reproductive failure. A species can be huge and still vulnerable to environmental change. A population can dominate a landscape and still disappear when climate, vegetation, or geography shifts. Gigantism is a strength under some conditions and a burden under others. This may help explain why the largest land animals did not simply keep getting larger forever. Evolution has no direction toward maximum size. Once a body reaches a certain scale, the costs become severe. More food is required. Growth takes time. Reproduction must replace losses. Heat balance becomes harder. Movement over poor ground becomes riskier. Predation on juveniles can still be intense. The upper edge of size is not a prize sitting open. It is a narrow zone where benefits and costs nearly meet. For sauropods, that zone was reachable because of their unique combination of traits. Mammals have never matched them on land. The largest extinct land mammals were immense, but they did not reach the same confirmed or likely masses as the greatest sauropods. Mammals carry different reproductive constraints, different neck anatomy, different respiratory systems, and different feeding mechanics. This does not make mammals inferior. It means sauropods found a body plan that opened a different size ceiling. The absence of chewing in sauropods is sometimes misunderstood. Chewing is efficient for processing food before it enters the gut, and mammals use it with great success. But chewing takes time and requires heavy skulls, large jaw muscles, and complex teeth. Sauropods followed another path. They cropped food rapidly with lighter heads and processed it internally. For an animal with a very long neck, keeping the head light may have mattered more than chewing efficiency at the mouth. This feeding strategy also fits a world where plant material could be abundant even if individual leaves or branches were not highly nutritious. A sauropod did not need to select only the best parts if it could take in enough volume and digest it over time. Its digestive system was likely vast, and the microbial breakdown of plant matter would have done much of the work. The animal was, in a sense, a moving fermentation chamber supported by a skeleton adapted for scale. We should be cautious about details such as gastroliths or stomach stones. They have often been associated with sauropod digestion, but the evidence for how important they were varies and remains debated. Some stones found with sauropods may have aided processing. Others may not be directly connected. The larger point is that sauropods processed plant matter mostly after swallowing rather than through intensive chewing. The exact mechanics of that internal processing are still reconstructed through comparison and inference. The mouth, though small, mattered. Tooth shape varied across sauropods and titanosaurs. Some had narrow crowns suited for stripping foliage. Replacement rates could be high in sauropods, allowing worn teeth to be shed and renewed. Feeding on tough or abrasive plants wears teeth quickly, and a large herbivore cannot afford a failed mouth. In the fossil record, teeth can reveal diet, feeding style, and sometimes replacement patterns that skeletons alone would miss. A Patagotitan skull is not known in the complete way we would want, but related titanosaurs help frame its likely appearance. The head would have been small compared with the body, the teeth simple, the jaws practical. In a living animal, the head might seem almost delicate at the end of the neck. This contrast is central to sauropod design. A massive body supports reach, and the lightweight head makes that reach possible. At the end of a long day, a giant herbivore might stand with food moving through its gut, heat leaving slowly from its body, and insects gathering around disturbed plants and dung. It would not need to sleep the way a human sleeps, or rest in a way we can reconstruct clearly. It may have rested standing or lowered itself carefully, depending on age, terrain, and behavior. The fossil record gives little certainty here. But the body had to recover. Even giants have ordinary needs. Resting at such size raises mechanical questions. How often did the largest Titanosaurs lie down? How easily could they rise? What ground was safe? Modern large animals can rest in different postures, but sauropod anatomy was different. Trackways and rare resting traces from sauropods elsewhere can help, but the behavior of Patagonia's giants remains uncertain. The safest reconstruction allows that they rested, but does not pretend to know exactly how often or how long. Water use also remains partly inferred. Large animals need water, though the amount depends on physiology, diet, climate, and behavior. Floodplain habitats provided access, but dry intervals could create stress. A giant animal drinking at a river would be vulnerable not because a predator could easily kill it, but because footing, crowding, and awareness all matter near water. River margins are productive and dangerous at the same time. Imagine an adult titanosaur stepping down a bank. The front foot tests soft sediment, the body weight shifts, mud compresses, water clouds around the toes. A smaller animal moves away. Somewhere nearby, a predator watches without committing. The giant lowers its head, drinks, lifts again, and stands with water falling from its jaws. Nothing happens. And that is the point. Survival is often a series of moments in which nothing goes wrong. Moments where nothing goes wrong rarely fossilize. Paleontology is filled with death because death leaves bodies. It is filled with floods because floods bury. It is filled with bones because soft tissue disappears. The living majority of the dinosaur age was ordinary activity beyond preservation. Feeding without death. Walking without tracks that endure. Nesting without eggs preserved. Years of movement and growth erased because the conditions were not right. This absence can make the fossil record feel grim, but it should also remind us how much life surrounded every fossil event. A bone bed is not the whole ecosystem. It is a punctuation mark. Around it were countless days that left no mark at all. The giants of Patagonia lived through those unrecorded days. The fossils are only the few pages that did not burn. Some of those pages are still in the ground. Patagonia's exposures are extensive, and new material continues to appear. But discovery is not only a matter of luck. It depends on trained eyes, funding, access, collaboration, weather, preparation facilities, and legal protections. A world-class fossil can be found only if there is a world capable of recognizing and preserving it after discovery. The human side of the story includes ranch workers, technicians, students, scientists, drivers, preparators, museum staff, illustrators, and communities living near the fossil sites. The animals are ancient, but paleontology is modern and social. A giant skeleton in a museum may look like the achievement of one discovery, but it is usually the result of many people's labor spread across years. The name on the paper is only part of that network. Fieldwork also depends on trust with landowners and local knowledge. The Mayo family's role in the Patagotitan discovery is preserved in the species name, but the broader point applies widely. Fossils are found in lived landscapes, not empty scientific zones. Ranches, roads, towns, and protected areas all intersect with ancient rocks. The relationship between science and place is practical, ethical, and ongoing. Argentina has produced some of the most important dinosaur discoveries of the last several decades, and Patagonia remains central to that record. The discoveries are not only exports of spectacular fossils to global attention, they are part of Argentine science, museums, education, and regional identity. The best telling of these giants should keep them connected to the land and institutions that revealed them. This is especially true because the history of paleontology has often involved fossils being removed from their countries or regions of origin with little benefit to local communities. Modern work increasingly emphasizes collaboration, local stewardship, and keeping discoveries accessible where they are found. Patagonia's giants belong to science, but they also belong to the landscapes and communities that hold their history. The public mounts displayed around the world can inspire awe, but the original fossils and their contexts remain central. A cast can travel. A quarry cannot. A cast can show the body. The quarry shows the death, burial, and environment. Both are valuable, but they do different things. The museum hall introduces the animal. The field site explains why the animal is known. Even the word Patagonia covers a huge region, spanning southern Argentina and Chile, with varied geology, climates, and histories. The giant titanosaurs discussed here come primarily from Argentine Patagonia and related basins. It is useful to speak of Patagonia as a broad fossil region, but precision matters. Chubut is not Nucun. Santa Cruz is not Rio Negro. Each province, basin, and formation gives a different part of the story. When we move from La Flecha to the Huincul Formation, we move not only across geography, but across time and ecology. When we move from Argentinosaurus to Dreadnoughtus, we cross millions of years and major differences in preservation. The mind can gather all the giants into one procession, but the rocks keep them separated. A good reconstruction lets them stand together as a theme while keeping their individual settings intact. This is why a script about giants can move broadly without becoming a generic overview of the Mesozoic. The focus remains on Patagonia, Titanosaurs, gigantism, and the evidence that lets us reconstruct them. Other dinosaurs enter because they shared ecosystems, hunted juveniles, scavenged carcasses, or reveal regional faunas. Plants enter because they fed the giants. Rivers enter because they buried them. Ash enters because it dates them. Nothing is background for long. The body of a titanosaur is the center, but the world is the frame that makes the body meaningful. A femur alone says size. A femur in a formation says time. A femur with other individuals says population. A femur near flood deposits says burial. A femur compared with other titanosaurs says evolution. The more context we keep, the more enormous the animal becomes in the right way, not inflated, but connected. The context also keeps the script from becoming a contest. Contests end with a winner. Science often ends with better questions. Was Patagotitan the heaviest? Perhaps not with certainty. Was Argentinosaurus larger? Possibly, but fragmentary. Was Dreadnoughtus still growing? The evidence suggests so. Did multiple giant titanosaurs live in Patagonia across the Cretaceous? Yes, that pattern is richer than a single crown. A crown would be too small for them anyway. These animals do not need the language of kings. They need the language of bodies, landscapes, and time. The largest sauropods were not rulers in a human sense. They were herbivores. Their power was ecological, not political. They shaped vegetation, moved nutrients, fed predators and scavengers, and occupied space at a scale that changed how other animals lived around them. A juvenile walking behind an adult would see that power as shelter. A predator might see it as frustration. Insects would see dung and decay. Plants would respond to browsing and disturbance. Rivers would record the feet if the mud was right. The ecosystem did not admire the titanosaurs. It used them, resisted them, depended on them, and eventually absorbed them after death. The idea of absorption may be the most accurate ending for any dinosaur. The body returns to the system. Flesh to scavengers and microbes. Minerals to soil and water. Bones to sediment if conditions allow. In rare cases, those bones become fossils. In rarer cases still, they are found, studied, named, and mounted. The giant does not remain whole. It becomes many things before it becomes evidence. That transformation is not a loss from the perspective of Earth. It is the way life continues. The Cretaceous floodplain did not pause because a titanosaur died. Plants grew through the next season. Rivers moved. Predators hunted. Eggs hatched. Other giants kept walking. The fossil that means so much to us was only one event in a world that moved on immediately. From our side of time, though, the event becomes a doorway. We enter through the bone and find not one animal, but an entire system. The door opens onto titanosaurs, predators, plants, basins, floods, ash, eggs, tracks, museums, and uncertainty. It opens onto the largest land animals known and the delicate processes that allowed us to know them at all. A doorway can be narrow and still lead into something vast. The vastness is why these fossils continue to matter beyond size records. They teach anatomy at the edge of scale. They show how sauropod traits persisted into the Cretaceous. They reveal the distinctive dinosaur worlds of southern continents. They connect field geology with public wonder. They remind us that the fossil record is not evenly distributed, but where it is generous, it can change how the entire history of life is imagined. They also remind us that deep time is not empty time. 100 million years is not a blank distance between then and now. It is filled with sedimentation, erosion, evolution, extinction, climate change, mountain building, ocean opening, and the slow recycling of matter through living systems. The bone in the museum crossed all of that. Its survival is almost as improbable as the animal's size. If the script begins with a bone, it has to keep returning to bone, because bone is the bridge. The neck in the imagination comes from cervical vertebrae. The weight estimate comes from limb bones. The movement comes from joints and tracks. The growth comes from microscopic bone tissue. The ecosystem comes from bones found with other fossils in sediment. Every visual reconstruction should remain accountable to these physical anchors. This accountability does not reduce atmosphere. It creates it. A river is more vivid when it is tied to sandstone and siltstone. A flood is more powerful when it explains a bone bed. A herd is more plausible when multiple individuals and trackways make group movement possible. A predator is more interesting when its presence comes from teeth, skulls, and related formations rather than a need for action. Evidence gives the images weight. Weight is the word that keeps returning. Weight in the limb bones. Weight in the tracks. Weight in the museum hall. Weight in the years of fieldwork. Weight in the uncertainty of a missing skeleton. Weight in the idea that land life once pressed so hard into mud that traces of its passing could outlast mountains. The giants of Patagonia are not only long or tall, they are heavy in every sense. And yet the final impression is not heaviness alone. It is balance. Bones lightened by air. Necks balanced by tails. Massive bodies supported by columnar limbs. Ecological costs balanced by feeding efficiency. Scientific wonder balanced by caution. Public scale balanced by local context. These animals existed because many balances held long enough for them to live. When those balances failed, individuals died. When global balances failed at the end of the Cretaceous, the non-avian dinosaurs disappeared. But before that ending, Titanosaurs had a long run. They were not evolutionary mistakes waiting to collapse. They were successful animals in successful ecosystems, and Patagonia preserves some of their most extraordinary evidence. That evidence does not speak loudly. It waits. It waits in field jackets, drawers, quarry walls, museum halls, and papers. It waits for someone to ask a better question. Not only how big, but how known. Not only how heavy, but how supported. Not only what name, but what place. Not only what animal, but what world. The world keeps becoming more detailed. A formation once broadly dated becomes better constrained. A fragment once ignored gains meaning through comparison. A digital model tests a posture. A thin section reveals growth. A new expedition finds another bone. The giants become less like silhouettes and more like animals, not because imagination has increased, but because evidence has. Evidence also changes the emotional tone. The more we know, the less we need to make the past melodramatic. A titanosaur feeding quietly beside a channel is enough. A young animal crossing mud behind larger bodies is enough. A flood burying bones in separate events is enough. A femur emerging from desert rock is enough. The real story does not require the giants to be monsters. It only requires them to be themselves. They were themselves for millions of years. The names differ, the formations differ, the sizes differ, but the broad presence of titanosaurs across Patagonia's Cretaceous record shows a lineage doing what evolution had prepared it to do. Eat plants at scale, grow large where conditions allowed, move through landscapes shaped by rivers and climate, leave behind bones that would one day become questions. The questions remain open in the rock. Somewhere, perhaps, there is a more complete Argentinosaurus. Somewhere, a skull of a giant titanosaur may wait in a layer not yet exposed. Somewhere, a trackway may reveal group movement with more clarity than any bone bed. Somewhere, a new species may revise the map of titanosaur relationships. The past is gone, but the record of it is not finished. This unfinished record is what makes Patagonia feel alive to paleontology. The land is not only a place where famous dinosaurs have already been found, it is a place where the next discovery may change the famous ones. Every exposed slope carries possibility. Every weathered hill has a surface story and a hidden one. The giants already known are landmarks, not final boundaries. So the story can return, without closing too tightly, to the first exposed curve in the desert floor. A piece of bone seen through dust. A shape that does not belong to the modern landscape but has become part of it. The animal is gone. The ecosystem is gone. The river that buried it is gone. Yet the curve remains, and from that curve an entire Cretaceous world can be rebuilt with care. Another way to see the giants is through absence. For all their size, the largest titanosaurs are often known without the parts that would make them feel most complete to us. A skull is missing. A tail series is incomplete. The hands and feet may be partial. The neck might be known in one animal, but not another. This absence is not a minor inconvenience. It shapes the whole way the animals are understood. A painting can fill in the missing head, a mount can complete the missing tail, and a life reconstruction can place skin over the body, but the scientific animal remains a mosaic of known and inferred parts. That mosaic is still powerful because the known pieces are so informative. A femur can speak of mass. A cervical vertebra can speak of reach. A dorsal vertebra can reveal air spaces and the structure of the torso. A pelvis can show how the hind limbs were braced. A partial skeleton can become a strong reconstruction if the missing parts are supplied cautiously from close relatives. The viewer may see one seamless dinosaur, but the researcher sees confidence changing from bone to bone, high in one region, lower in another, always tied to what the fossil actually preserves. This is why the best reconstructions of titanosaurs often include uncertainty even when they appear visually complete. The curve of the back, the thickness of the neck, the exact depth of the torso, the amount of soft tissue around the tail base, the posture of the limbs, and the shape of the feet can all be modeled in more than one plausible way. For smaller animals, these differences may not change the final image dramatically. For the largest sauropods, they can change the mass estimate by many tons. A slightly deeper torso on an animal 30 meters long is not a small addition. It is a volume large enough to matter. The same is true for the neck. A reconstruction that adds muscle conservatively will differ from one that gives the neck a heavier profile. Both may be defensible within limits, and both may produce different impressions of the living animal. This is not artistic confusion. It is the reality of reconstructing a creature whose soft tissues disappeared almost completely and whose closest living relatives are birds and crocodilians, neither of which resembles a giant sauropod in overall body form. The closest living relatives are useful because dinosaurs sit within Archosauria, the group that includes crocodilians and birds. But titanosaurs were not halfway between a crocodile and an ostrich. They were their own lineage, separated by immense time and specialization. Birds help us understand air sacs, growth, eggs, and some aspects of dinosaur ancestry. Crocodilians help frame parts of archosaur biology and soft tissue inference. But a titanosaur body is not directly copied from either. Its size changes the rules. A small bird's skeleton can be pneumatic because flight demands lightness. A sauropod's skeleton can also be pneumatic, but for a different functional outcome, reducing weight in a land animal that had no intention of flying. A crocodile may help with some muscle reconstructions, but a crocodile sprawls close to the ground while a sauropod stands on columnar limbs. The living animals are guides, not templates. The extinct animal has to be allowed to remain strange where the evidence makes it strange. The strangeness becomes clearer when the body is considered from the inside outward. The torso had to hold a vast digestive tract, lungs connected to air sacs, a powerful circulatory system, reproductive organs, and muscles large enough to move the limbs. The heart of a giant sauropod has not fossilized, and its exact structure remains unknown, but blood still had to move through the animal. If the head was raised high, circulation had to meet that challenge. If the neck was held lower much of the time, the challenge changed but did not vanish. The body had to regulate pressure, oxygen, heat, and metabolism across a scale no modern terrestrial vertebrate reaches. These are not decorative physiological questions. They are central to whether the animal could live. The fossil bones are the strongest evidence, but the missing organs had to function every moment the animal was alive. A mounted skeleton may look clean and spare. The living animal was full, heavy, warm, wet, and internally active. Because soft organs are missing, paleontologists use constraints. The rib cage gives an approximate boundary. The vertebral column shows where air sacs entered bone. The pelvis and limb proportions indicate how the body mass was distributed. Trackways can suggest stance width and foot placement. Growth tissues reveal how fast bone was being laid down. No one line of evidence recreates the full physiology, but together they create a range of possible animals and rule out others. A giant titanosaur could not be reconstructed with a thin body like a long-necked greyhound because the ribs and pelvis do not allow it. It could not be reconstructed with solid, heavy vertebrae because the fossils show pneumaticity. It could not be treated like a scaled-up lizard because its posture, growth, and respiratory anatomy point elsewhere. Scientific reconstruction is partly imagination, but it is imagination fenced by anatomy. The same fence applies to behavior. It is possible to imagine a herd migrating across Patagonia in a grand seasonal movement, but the evidence for any particular migration route may be absent. It is possible to imagine adults guarding nests, but titanosaur nesting evidence does not automatically prove that kind of parental care. It is possible to imagine coordinated defense against predators, but a bone bed alone cannot demonstrate it. The responsible approach is not to strip the animals of behavior, but to grade the behavior according to evidence. Feeding is certain. Growth is certain. Reproduction through eggs is certain for titanosaurs broadly. Movement across landscapes is certain. Grouping is possible in some contexts and likely in others, depending on tracks and bone associations. Complex social care remains much harder to prove. This restraint fits the animals better than overconfident storytelling, because the real past was not arranged for our preferred scenes. Yet restraint does not mean the animals were dull. The ordinary behaviors of a giant titanosaur are already extraordinary at full scale. Feeding becomes landscape disturbance. Walking becomes track formation. Drinking becomes a negotiation with mud and gravity. Reproduction becomes the contrast between small eggs and immense adults. Growth becomes the long transformation of a vulnerable hatchling into an animal few predators could threaten. Even standing still becomes biologically interesting because heat, blood pressure, balance, digestion, and breathing continue inside the body. The drama is not in constant conflict. It is in the fact that such a body could be maintained hour after hour, season after season, in a real ecosystem. A calm sauropod is not an absence of action. It is a vast amount of biology working successfully. The largest titanosaurs also force us to think about population size. A landscape can support only so many animals that large, Even if sauropods needed less food per kilogram than smaller animals because of scaling effects, the total demand of each individual remained enormous. A viable population requires enough adults to reproduce, enough young to replace losses, and enough habitat to support them through good years and bad. This means giant titanosaurs were tied to large-scale environmental productivity and movement across space. A single valley might not be enough during a dry interval. A river system, basin, or broader landscape may have been necessary. The fossils we find at one locality could represent animals using only part of a much larger range. A quarry is a window, not a fence around the animal's world. Population thinking also changes how we interpret rarity. A fossil of a giant may be rare because the animal itself was rare, or because its preferred habitat did not preserve well, or because its bones were hard to expose, collect, and identify, or because the formation has not been searched enough. Conversely, a bone bed with multiple individuals may indicate local abundance, repeated use of a site, or a preservation trap, not necessarily high population density across the whole region. These distinctions matter when discussing the ecology of the giants. A species can be ecologically important even if its fossils are uncommon. A species can be well represented at one site because death and burial were unusually favorable there. The rock record is not a census. It is a biased archive that becomes clearer only when its biases are studied. The idea of a biased archive is especially important for the largest dinosaurs because their bones are both easier and harder to find. They are easier because a huge femur or vertebra can weather out visibly, drawing attention from a distance. They are harder because complete skeletons are difficult to preserve, excavate, transport, and prepare. A small animal might be preserved whole in a fine-grained deposit. A giant body is more likely to fall apart, scatter, and enter the record in pieces. Its size increases the chance that at least some part survives, but decreases the chance that everything remains together. This is one reason the largest animals often come to science as fragments with enormous implications. The fossil record gives us enough to feel the animal's scale, then withholds the very completeness that would answer our next questions. There is also a difference between largest species and largest individual. When we speak of Patagotitan, Argentinosaurus, or Dreadnoughtus, we are usually discussing species known from particular fossils, not every individual that ever lived. The largest known individual of a species may not be the largest individual the species ever produced. Modern animals vary. Some elephants are larger than others. Some whales exceed typical size. Dinosaurs would have varied too, through sex, age, nutrition, health, and genetics. If the known Patagotitan individuals were young adults, older individuals might have been larger. If the known Argentinosaurus bones came from an especially large individual, the species average might have been smaller. Without large samples, these questions remain open. The biggest dinosaur ever found is not necessarily the biggest dinosaur that ever lived, and the biggest dinosaur that ever lived may never have fossilized. This does not make the rankings meaningless, but it does put them in perspective. Rankings are snapshots of current evidence. They help organize knowledge and attract attention, but they should not become the whole story. The top of the size chart is unstable because it depends on new discoveries, revised estimates, and the difficult comparison of incomplete animals. A more complete but slightly smaller specimen may be scientifically more valuable than a larger fragment. A fragmentary giant may still be biologically important because it proves that a lineage reached a certain scale. Each type of fossil has a different kind of value. The healthiest view of Patagonia's giants holds both ideas at once. The rankings are fascinating, and the science behind them is more important than the rankings. The science behind them reaches into classrooms, museum halls, field camps, and laboratories. A visitor may first encounter Patagotitan as a skeleton too large for a single glance. A student may encounter it as a data point in sauropod body mass evolution. A preparator may know it as hours of tool work under magnification. A geologist may think of the ash layers and river deposits. A local guide may connect it to Chubut, and the history of discoveries in the region. A child may simply feel small and remember the feeling for years. None of these encounters is wrong. They are different ways a fossil leaves the rock and enters human life. The most lasting encounter may be the quietest one. Not the headline, not the record claim, not the first moment under the museum mount, but the realization that the animal was real in a way that resists spectacle. It had no obligation to amaze us. It lived in heat and mud, among plants and other animals, under weather it could not control. Its bones became fossils through chance and process. Its name arrived long after its death. The wonder is not that the animal seems impossible. The wonder is that it was possible, and that a fragment of that possibility survived long enough to be recognized. There is another reason these animals hold attention so strongly. They force the human mind to move between scales that usually remain separate. At one scale, there is a person kneeling beside a bone, using a brush or an air tool, concerned with a crack only a few millimeters wide. At another scale, there is a skeleton that fills a hall and requires steel support to suggest the posture of a living body. At another, there is a floodplain measured in kilometers, where a herd might move between channels and feeding grounds. At another, there is Gondwana, breaking apart over tens of millions of years, changing coastlines, climates, and the routes available to animal populations. At another, there is evolution itself, preserving some traits, modifying others, allowing sauropods to remain successful long after the Jurassic icons had vanished. A titanosaur femur belongs to all of these scales at once. It is a physical object that can be measured on a table, but it also points outward to a body, a population, a landscape, a lineage, and a continent in motion. This is why a single fossil can hold so much narrative weight without needing to be exaggerated. The object is local and specific, but the implications are enormous. It begins in one place in the ground and expands until it touches almost every part of the ancient world around it. The giants also change how we think about absence in the modern world. Nothing alive on land gives a true comparison. Elephants are immense, but they do not approach the largest sauropods. Giraffes have long necks, but their proportions and constraints are different. Rhinoceroses, hippos, and extinct giant mammals show other ways to be large, but none recreate the sauropod solution. This means that when we imagine Patagotitan or Argentinosaurus, we cannot simply enlarge a familiar animal. We have to accept a body plan with no living equivalent, and that makes the reconstruction more demanding. The animals are not alien because they violate nature. They are alien because nature no longer uses this particular design. Their lineage ended. Their ecological role vanished. Their body plan, once widespread and successful, now survives only in stone, trackways, eggshell, and the distant inheritance of birds through a different dinosaur branch. The absence is part of the wonder. Modern land ecosystems can be rich, beautiful, and powerful, but they do not contain a 30-meter herbivore moving through trees. The empty space where such an animal might stand is a reminder that the present is only one version of what life can be. Even so, the ancient world should not be treated as a better world or a lost paradise. It was simply another world, with its own pressures and failures. Titanosaurs died in floods, droughts, disease, predation, and accident. Young animals were taken. Eggs failed. Ecosystems changed. Lineages disappeared. The Cretaceous was not designed for the comfort of its giants any more than the modern world is designed for the comfort of elephants or whales. Life persisted because enough individuals survived long enough to reproduce, not because the world was gentle. This makes the success of the Titanosaurs more impressive. They flourished not in an idealized landscape, but in changing basins, under seasonal stress, among predators, within ecosystems that rewarded some strategies and punished others. Their size was not a guarantee. It was a strategy with costs, and for a long time in Patagonia and across much of the Cretaceous world, the benefits were great enough. When we look at the bones, we are not looking at symbols of invincibility. We are looking at evidence of a strategy that worked until the conditions that supported it no longer did. Return to the femur. It lies partly out of the ground, pale against the sediment. Before anyone gives it a name, before any number is attached, before any museum hall fills with visitors, it is simply evidence, heavy, weathered, incomplete, enough to stop a person walking by, enough to bring scientists into the field, enough to reopen a world. Around that bone, the modern wind moves across the ranch. It carries dust, not the humid breath of the Cretaceous floodplain. The rivers that buried the animal are gone or changed beyond recognition. The plants are different. The predators are gone. The Titanosaurs are gone. But the ground still holds the consequence of their bodies. It still remembers weight in the only way stone can remember. 100 million years earlier, the same place was not empty. A channel curved through low ground. Plants grew along its banks. Insects moved through warm air. Turtles and crocodiliforms occupied water and mud. Theropods crossed the open spaces. Somewhere nearby, one of the largest animals the land has ever supported lowered its head to feed, shifted its weight, and stepped forward. The foot pressed into the floodplain. The body moved on. The track filled, the surface changed, the season turned, and eventually even the bones entered the ground. Nothing about that moment knew it would become evidence. Nothing about the animal knew it would become a name. It was only life, immense and ordinary, passing through Patagonia. In the end, that may be the most important thing the giants tell us. The biggest dinosaurs ever found were not built to amaze us. They were built by evolution to live where they lived, to feed, to grow, to reproduce, to survive long enough for their lineage to continue. Their size became wonder only after they were gone. The bone remains in stone. The desert wind moves over it. A hand clears the dust. The giant does not return, but the world that held it opens for a moment, wide enough to show a river, a floodplain, a herd of titanosaurs, and the quiet truth of land animals larger than anything alive today.